Have you ever looked up at the night sky and wondered what truly connects the countless points of light scattered across the darkness? What invisible force binds together the billions of galaxies that populate our universe? Look up, and you'll see stars. Look farther, and you'll find galaxies. But between them, between everything you can see, is something more. Not darkness, not emptiness, but a pattern, a thread, an invisible weave of gravity and matter, binding galaxies together across the silence. Tonight, we follow it not with our eyes, but with our imagination. This is the invisible thread between every galaxy. As we drift through the cosmos tonight, we'll explore the hidden architecture that shapes our universe. We'll discover how galaxies aren't just randomly scattered, but follow an intricate pattern, a cosmic web that extends across billions of light years. Though we cannot see this web directly, scientists have mapped its existence through careful observation and powerful simulations. It is the quiet scaffolding of existence, a whisper holding the stars in place, including our own Milky Way. Join us as we journey through this unseen reality, where dark matter forms vast filaments stretching across the cosmos, creating highways along which galaxies travel and cluster. A place where empty voids grow between these threads, shaping the structure of everything we can observe. This is the true shape of our universe, not just what we see, but what we've come to understand. What if I told you that the universe has a shape you cannot see, a structure that extends across billions of light years, invisible to our eyes, but fundamental to everything we observe? This is the cosmic web, the largest structure in existence. When astronomers first began mapping distant galaxies, they expected to find them scattered randomly throughout space. The universe, they reasoned, should be roughly the same in all directions, uniform, homogeneous, without pattern. But as telescopes improved and surveys expanded, a surprising truth emerged. Galaxies weren't distributed randomly at all. They formed clusters, and these clusters formed larger structures, like a three-dimensional spiderweb stretching across the cosmos. Imagine pouring cream into your coffee. At first, the cream forms distinct streams and swirls. Over time, these patterns fade as the cream diffuses. The early universe was like perfectly mixed coffee, uniform and smooth, but something remarkable happened. Instead of remaining uniform, tiny quantum fluctuations, microscopic variations in density, were stretched to cosmic scales during a period of rapid expansion called inflation. These subtle differences in density grew over billions of years, as gravity pulled matter toward regions that were already slightly denser than their surroundings. Where there was slightly more matter, gravity pulled in still more matter. Where there was slightly less, matter flowed away. What began as small ripples evolved into a vast cosmic architecture, a network of filaments, sheets, and nodes that we call the cosmic web. This web consists of dense clusters of galaxies connected by filaments driver-like streams of matter, stretching tens or hundreds of millions of light years. Between these filaments lie vast voids, enormous bubble-like regions nearly empty of galaxies. This pattern repeats across the observable universe, creating a foam-like structure on the grandest scales. But here's what makes this structure truly remarkable. Most of it consists of dark matter, a mysterious substance that neither emits nor reflects light. We can only detect it through its gravitational effects. The galaxies we see are merely bright markers, tracing this invisible scaffolding, like lights strung along unseen wires. Think of the cosmic web as the skeleton of the universe. Just as our bones give structure to our bodies while remaining hidden beneath our skin, dark matter provides the framework upon which galaxies form while remaining invisible to our telescopes. The revelation of this structure changed our understanding of the cosmos. The universe is not a random scattering of galaxies, but a complex, interconnected system with a distinct architecture. Galaxies form along the filaments of this web like pearls on a string. They cluster at the nodes where filaments meet, and they are conspicuously absent from the vast voids between. This structure tells us something profound about the forces that shape our universe. Gravity, acting over billions of years on the slightest initial irregularities, has sculpted matter into this intricate pattern. What began as nearly perfect uniformity has evolved into beautiful complexity, a network, binding together everything we observe. When we look at maps of the cosmic web, we are seeing the largest structure in existence, a pattern extending across billions of light years. And perhaps most remarkably, We are seeing a structure that has evolved over the entire history of the universe, a living record of cosmic evolution from the Big Bang to the present day. As our understanding of this cosmic architecture has grown, so too has our appreciation for its complexity. The filaments themselves have structure. They are not uniform tubes of matter, but complex, braided streams with varying density. Some are straight, others curved. Some are thick, others thin. And they interconnect in a three-dimensional lattice that defies simple description. Astronomers classify the components of the cosmic web into four distinct categories. First are the clusters-dense knots, where multiple filaments converge, home to hundreds or thousands of galaxies. Then come the filaments themselves, cosmic highways stretching between clusters. Sheets or walls are flat, pancake-like structures, where matter has collapsed in one dimension. And finally, the void's vast expanses nearly devoid of visible matter. This classification helps us understand the dynamics of cosmic evolution. Matter flows from voids into sheets, from sheets into filaments, and from filaments into clusters, a cosmic hierarchy of structure. And this flow continues today, albeit slowly, as the universe continues to evolve. What makes this structure even more remarkable is how it emerged from near-perfect uniformity. The cosmic microwave background radiation, the oldest light in the universe, dating from just 380, 0 years after the Big Bang, shows temperature variations of only about 1 part in 100, 0. These tiny fluctuations were the seeds from which all cosmic structure grew. From such subtle beginnings came the rich complexity we observe today. The discovery of the cosmic web has profound implications for our understanding of galaxy formation and evolution. Galaxies are not isolated systems, evolving independently. They are connected by the web, influenced by their position within it. Galaxies in dense clusters evolve differently from those in isolated regions. The flow of gas along filaments fuels star formation and shapes galactic properties. Consider our own Milky Way. It resides in a small cluster called the local group, which itself sits within a filament of the cosmic web. This filament is part of a larger structure called the local sheet, which is one small component of the Laniakea supercluster. Our cosmic address includes not just our location in space, but our position within this vast cosmic network. The tools we use to map this invisible structure have grown increasingly sophisticated. Galaxy surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the three-dimensional distribution of visible matter. Computer simulations model the evolution of dark matter under the influence of gravity, producing virtual cosmic webs that match our observations with remarkable accuracy. One particularly powerful technique is weak gravitational lensing, the slight distortion of light from distant galaxies as it passes through the gravitational field of intervening matter. This allows astronomers to directly map the distribution of dark matter, revealing the full extent of the cosmic web, not just the visible galaxies that trace it. What's truly humbling is the scale of this structure. The filaments of the cosmic web can stretch for hundreds of millions of light years. The largest known void, the Boötes void, spans about 330 million light years in diameter region, so vast it would take light itself more than 300 million years to cross. These are scales that challenge our comprehension, reminding us of the vastness of the cosmos and our small place within it. Yet there is comfort in this connection. We are not isolated in the universe. Our galaxy, our solar system, our planet all are part of this grand cosmic network. The same forces that shape the largest structures in the universe also govern the motion of planets around stars and the orbit of moons around planets. There is a continuity of physical law across all scales. As we continue our journey through the invisible threads connecting galaxies, remember that what we cannot see often shapes what we can. The cosmic web may be invisible to our eyes, but its influence is everywhere. It is the architectural blueprint of the universal design, not imposed from without, but emerging from within, through the simple action of gravity on primordial irregularities. In the chapters that follow, we'll explore how dark matter weaves this web, how galaxies flow along its filaments, and how this structure continues to evolve as the universe expands. But for now, contemplate the hidden architecture all around us, the invisible shape of a universe far more structured and interconnected than it first appears. Have you ever wondered what truly holds our universe together? What invisible force shapes the cosmic landscape we observe? The answer lies in one of the greatest mysteries of modern astronomy: dark matter. Dark matter is the silent architect of the cosmic web, the unseen backbone supporting all structure in our universe. Though we cannot detect it directly with our instruments, we know it must exist through its gravitational influence, and without it, the magnificent cosmic web we've begun to explore simply could not exist. When astronomers first calculated the mass of galaxies based on the visible stars, gas, and dust they contain, they encountered a puzzling discrepancy. Galaxies were spinning too fast for their visible matter to hold them together. By all accounts, they should have torn themselves apart billions of years ago. Something invisible was providing the extra gravitational glue, something that outweighs visible matter by roughly 5-to-1. This mysterious substance was named dark matter. Unlike ordinary matter, the protons, neutrons, and electrons that make up everything familiar to us, dark matter does not interact with light or other forms of electromagnetic radiation. It passes through ordinary matter like a ghost, detectable only through its gravitational pull. Yet this elusive substance comprises approximately 26% of the total mass-energy content of our universe, compared to just 4% for ordinary matter. Dark matter's most profound impact lies in its role as the primary architect of cosmic structure. In the early universe, ordinary matter was too hot and energetic to clump together under gravity's influence. But dark matter, immune to the pressure of radiation, began gathering into clumps and filaments almost immediately after the Big Bang. These dark matter concentrations created gravitational wells that would eventually trap ordinary matter as the universe cooled. Imagine a vast, invisible scaffolding erected across space. As ordinary matter cooled after the Big Bang, it settled into this pre-existing framework, like morning dew collecting on a spider's web. The galaxies we see today formed where dark matter had already created dense nodes and filaments, following patterns laid down in the first few 100 million years of cosmic evolution. This sequence explains why galaxies form along filaments of the cosmic web. They're not creating these structures, they're tracing them, like lights strung along an invisible framework. The dark matter filaments were there first, and galaxies simply followed the path of least resistance, flowing along these cosmic highways toward the densest intersections. Computer simulations have been crucial in confirming this understanding. Projects like the Millennium Simulation and Illustris have modeled the evolution of dark matter structures from the early universe to the present day. Starting with tiny density fluctuations measured in the cosmic microwave background radiation, these simulations follow the gravitational interaction of billions of dark matter particles over cosmic time. The results are striking. Without any special adjustments, these simulations produce a cosmic web remarkably similar to what we observe in galaxy surveys. Dark matter naturally forms into filaments, sheets, and clusters under the influence of gravity alone. When the simulations include the physics of ordinary matter, galaxies form precisely where dark matter has created the densest regions, just as we observe in the real universe. The Millennium Simulation, completed in 2005, followed over 10 billion dark matter particles from shortly after the Big Bang to the present day. It revealed how dark matter forms into filaments and nodes across billions of light years, creating a cosmic web strikingly similar to what we observe in galaxy surveys. The Illustris project, a more recent simulation, incorporated not just gravity, but also the complex physics of ordinary matter, showing how galaxies form and evolve within this dark matter framework. What makes dark matter so effective at weaving the cosmic web is its unique properties. Unlike ordinary matter, it doesn't collide or interact with light or other particles. It experiences only gravity. This simplicity allows it to form structures unimpeded by the complex physics that affects ordinary matter. Dark matter particles pass right through each other, interacting only through their mutual gravitational attraction. This property allows dark matter to form denser concentrations than would be possible for ordinary matter. When ordinary matter collapses, it heats up, creating pressure that resists further collapse. But dark matter feels no such pressure. It can form dense halos around galaxies and extend into vast filaments connecting these halos across intergalactic space. These dark matter halos are crucial for galaxy formation. Every galaxy we observe sits within a much larger halo of dark matter, like a luminous island in a dark sea. Our own Milky Way galaxy is thought to reside within a dark matter halo several times larger than the visible disk of stars. This halo extends far beyond the visible galaxy, merging gradually with the dark matter filament that connects us to neighboring galaxy clusters. The largest dark matter structures are truly immense. Simulations suggest that some dark matter filaments may stretch across hundreds of millions of light years, forming cosmic highways along which galaxies and gas flow toward the densest regions. These dense regions, where multiple filaments converge, become the locations of galaxy clusters, the largest gravitationally bound structures in the universe. Yet for all its cosmic importance, dark matter remains profoundly mysterious. We don't know what it's made of. The leading theory suggests it consists of a yet undiscovered fundamental particle, perhaps a weakly interacting massive particle, or WIMP. These hypothetical particles would have mass but interact with ordinary matter only through gravity and possibly the weak nuclear force. Despite extensive searches using particle accelerators, underground detectors, and space-based observatories, we have yet to directly detect these particles. Dark matter remains known only by its gravitational effects, a cosmic sculptor whose hand we can see only in the structures it creates. This invisible weaver of the cosmic web reminds us of how much remains unknown about our universe. The galaxies we observe, with their billions of stars, constitute only the bright nodes in a much vaster network of matter. The true extent and structure of the cosmos is largely invisible to our telescopes, revealed only through its gravitational effects on what we can see. The story of dark matter begins in 1933, when astronomer Fritz Zwicky studied the Coma Cluster, a dense collection of over 1,000 galaxies. He measured how fast these galaxies were moving within the cluster and calculated that they were moving so quickly they should have escaped the cluster's gravitational pull. Something invisible was holding them together, something that provided far more mass than all the visible stars combined. Zwicky called this missing mass Dunkle Materie, dark matter. For decades, Zwicky's observations were largely ignored. It wasn't until the 1970s that astronomer Vera Rubin confirmed the existence of dark matter through detailed studies of galaxy rotation. She found that stars at the edges of spiral galaxies orbit the galactic center at much higher speeds than expected based on the visible matter alone. Again, something invisible was providing the extra gravitational pull. What makes dark matter so crucial for cosmic structure is its behavior in the early universe. Shortly after the Big Bang, the universe was a hot, dense soup of particles and radiation. Ordinary matter was tightly coupled to radiation, preventing it from clumping together under gravity. But dark matter, which doesn't interact with radiation, was free to begin forming structures. As the universe expanded and cooled, dark matter began to coalesce into a network of filaments and clumps. The denser regions attracted more dark matter, growing steadily over time. When the universe had cooled enough for ordinary matter to decouple from radiation about 380,000 years after the Big Bang, this ordinary matter began falling into the gravitational wells already created by dark matter. The result was a universe where structure formation was jump-started by dark matter. Without it, structure formation would have been delayed by hundreds of millions of years, potentially preventing galaxies from forming as we know them today. The cosmic web itself might never have emerged in a universe without dark matter. The role of dark matter in weaving the cosmic web is especially clear in computer simulations. When scientists run simulations without dark matter, using only the known physics of ordinary matter and gravity, the resulting universe looks nothing like our own. Galaxies do not form properly, and the web-like structure we observe is absent. Only when dark matter is included do the simulations produce a universe that matches our observations. These simulations have grown increasingly sophisticated over time. The original Millennium simulation has been succeeded by projects like Illustris, EAGLE, and Illustris TNG, each incorporating more detailed physics and higher resolution. These virtual universes allow scientists to watch cosmic history unfold from the Big Bang to the present day, revealing how dark matter shapes the evolution of structure across cosmic time. One particularly striking feature revealed by these simulations is the hierarchy of dark matter structure. The smallest dark matter halos may be just a few light years across, hosting no galaxies at all. Medium-sized halos host individual galaxies like our Milky Way. The largest halos contain entire clusters of galaxies. And these halos are not isolated, they're connected by filaments of dark matter that can stretch for hundreds of millions of light years. This hierarchical structure forms through a process of mergers and accretion. Smaller dark matter halos form first, then merge to create larger ones. This process continues throughout cosmic history, with small halos being absorbed into larger ones, creating the complex network of the cosmic web we observe today. Perhaps most fascinating is how dark matter determines where galaxies can form. Galaxies need cold gas to form stars, and this gas tends to flow along the dark matter filaments, eventually pooling in the dense halos. The largest galaxies form where multiple filaments intersect, providing a steady supply of fresh gas for star formation. This connection between dark matter and galaxy formation explains many observed patterns in the distribution of galaxies. The most massive galaxies tend to sit at the centers of dense clusters, where multiple dark matter filaments converge. Smaller galaxies often form along filaments, like beads on a string, and very few galaxies form in the vast voids between filaments, where dark matter is sparse. The influence of dark matter extends even to the shapes and properties of individual galaxies. Galaxies that form in isolation along dark matter filaments tend to be spiral galaxies, rich in gas and actively forming stars. Those that form at the dense nodes where filaments meet are more likely to be elliptical galaxies, with older stars and less ongoing star formation. This environmental influence, ultimately driven by the distribution of dark matter, helps explain the diversity of galaxies we observe. As astronomers develop new techniques to map the dark matter distribution, our understanding of the cosmic web grows ever more detailed. Weak gravitational lensing, the slight distortion of light from distant galaxies as it passes through the gravitational field of intervening dark matter, allows us to map the distribution of dark matter directly. These maps confirm what simulations have shown. Dark matter forms a vast cosmic web, with galaxies tracing its most prominent features. Yet for all we've learned about dark matter's role in cosmic structure, its fundamental nature remains one of the greatest mysteries in modern physics. Is it composed of a new type of elementary particle? Is it a manifestation of modified gravity? Could it be primordial black holes formed in the early universe? The search continues in laboratories around the world and in space-based observatories designed to detect the subtle signals dark matter might produce. What we do know with certainty is that dark matter's gravitational influence has shaped the universe we observe. It is the silent architect of cosmic structure, the invisible scaffolding upon which galaxies form. Without it, the universe would be a vastly different place, perhaps a nearly uniform sea of gas, without the rich structure of galaxies, clusters, and filaments we observe. As we continue our journey through the cosmic web, remember that we are exploring not just the visible universe of stars and galaxies, but a much vaster, invisible universe of dark matter. The luminous archipelagos of galaxies are merely bright markers of this deeper reality, a cosmic ocean of invisible matter that shapes everything we see. In the silence between stars and galaxies flows this dark current substance that neither emits nor absorbs light, yet exerts a gravitational pull that has shaped the evolution of the universe since its earliest moments. It is the thread that binds the cosmic web, the silent architecture underlying all structure in our universe. Have you ever wondered how galaxies know where to go in the vast emptiness of space? Why they gather in clusters, align in filaments, and avoid the great cosmic voids? The answer lies in how galaxies follow the invisible threads of the cosmic Weber journey we'll explore together now. Galaxies do not wander randomly through the cosmos. They follow paths laid out by the underlying dark matter structure, flowing along cosmic filaments like leaves carried by an invisible river. This choreographed movement shapes the large-scale structure we observe today and continues to evolve as the universe expands. When we map thousands of galaxies across vast regions of space, patterns emerge. These patterns are not random, but follow the underlying dark matter filaments of the cosmic web. Galaxies trace these filaments like pearls on an invisible string, clustering densely where filaments intersect and thinning out along their length. This distribution is not static, but dynamic. Galaxies are in constant motion, flowing along these dark matter highways toward the densest regions. The relationship between galaxies and the cosmic web begins with their birth. Galaxies form where gas can cool and condense within dark matter halos. The largest concentrations of dark matter, the nodes where multiple filaments intersect, become the sites of massive galaxy clusters. These clusters can contain thousands of galaxies bound together by gravity, swimming in a sea of hot gas and dark matter. Along the filaments connecting these clusters, we find smaller groups and individual galaxies. The filaments act as cosmic highways, channeling both dark and ordinary matter toward the clusters. Gas flows along these filaments, providing fresh fuel for galaxy formation and growth. The result is a cosmic ecosystem where a galaxy's properties and evolution are intimately tied to its position within the web. Consider our own cosmic neighborhood. The Milky Way resides in the local group, a small collection of galaxies that includes Andromeda and about 50 smaller galaxies. This entire group sits along a dark matter filament that connects us to the Virgo cluster, a much larger collection of galaxies about 54 million light-years away. This filament is part of a larger structure called the local sheet, which itself is just one component of the Laniakea Superclustera vast complex of galaxy clusters and filaments, spanning more than 500 million light-years. The movement of galaxies along the cosmic web is revealed through their redshifts, the stretching of light that indicates whether an object is moving toward or away from us. By measuring the redshifts of thousands of galaxies, astronomers have created three-dimensional maps that reveal not just where galaxies are, but how they're moving. These maps show a phenomenon called peculiar velocities movements that deviate from the overall expansion of the universe. While all distant galaxies are moving away from us due to cosmic expansion, they also have additional motions caused by the gravitational pull of nearby structures. These peculiar velocities reveal galaxies flowing along filaments toward clusters, like water flowing downhill. One dramatic example of this flow is the Great Attractora massive concentration of matter, about 150 million light-years away, that is pulling our local group and many other galaxies toward it at speeds of hundreds of kilometers per second. Beyond the Great Attractor lies an even more massive structure called the Shapley Supercluster, which may be responsible for even larger flows of galaxies across billions of light-years. These vast movements follow a simple principle. Galaxies flow from regions of lower density to regions of higher density, from voids to sheets, from sheets to filaments, and from filaments to clusters. This hierarchical flow is driven by gravity and follows the underlying dark matter distribution. But the journey along the cosmic web isn't always smooth. When galaxies fall into dense clusters, they encounter a hostile environment. The space between cluster galaxies is filled with hot gas that can strip away the cold gas from infalling galaxies, shutting down their star formation. Frequent interactions and mergers between galaxies and clusters can transform spiral galaxies into elliptical ones, changing their shape and composition. This environmental influence explains many observed patterns in galaxy properties. Spiral galaxies with their distinctive disk shape and active star formation are most common in the less dense regions of the cosmic web, along filaments and in small groups. In contrast, elliptical galaxies rounder, redder, and with less active star formation dominate in dense clusters. This pattern arises because a galaxy's journey along the cosmic web shapes its evolution. The alignment of galaxies with the cosmic web is particularly striking. Spiral galaxies tend to align their disks parallel to the filaments they inhabit, while the long axes of elliptical galaxies often point along the filaments. These alignments are not coincidental, but reflect how galaxies form and evolve within the cosmic web's gravitational influence. Massive galaxy clusters form at the nodes where multiple filaments intersect. These clusters contain thousands of galaxies, vast amounts of hot gas heated to millions of degrees, and enormous dark matter halos. The combined mass of these clusters can exceed a quadrillion times the mass of our Sun, making them the largest gravitationally bound structures in the universe. One of the most famous of these is the Coma Cluster, containing over 1,000 bright galaxies and thousands more smaller ones. Located about 320 million light-years away, it sits at the intersection of several major filaments of the cosmic web. Another example is the Perseus Cluster, one of the most massive objects in the known universe, with a mass of hundreds of trillions of solar masses. These enormous clusters anchor the cosmic web, serving as the main gravitational attractors toward which galaxies flow. The flow of galaxies along filaments is not just a theoretical prediction, it's observed directly in our cosmic neighborhood. The Virgo Cluster, The nearest large cluster to our local group is pulling us toward it along a filament. Our galaxy, along with many others in our vicinity, is slowly falling toward Virgo at speeds of several hundred kilometers per second. On even larger scales, astronomers have identified vast streaming motions called bulk flows, where entire regions of the universe, containing thousands of galaxies, move coherently in the same direction. These bulk flows can extend across hundreds of millions of light years and reach speeds of thousands of kilometers per hour. They represent the largest known movements in the universe and are direct evidence of the gravitational influence of the cosmic web on galactic motion. Redshift surveys have been essential in revealing these patterns. Projects like the Sloan Digital Sky Survey, the 2-degree Field Galaxy Redshift Survey, and more recently, the Dark Energy Survey have measured the positions and velocities of millions of galaxies. These surveys create three-dimensional maps that reveal the cosmic web in unprecedented detail. One particularly striking visualization comes from the Sloan survey, which revealed a structure called the Sloan Great Wallone, of the largest known structures in the universe, a vast complex of galaxies, clusters, and filaments extending for over 1.5 billion light-years. These immense structures are the most visible manifestations of the cosmic web and show how galaxies trace its contours across billions of light-years. The relationship between galaxies and the cosmic web is reciprocal. While galaxies follow the web's structure, they also influence it through their gravitational effects and feedback processes. Supermassive black holes at the centers of galaxies can eject enormous amounts of energy into their surroundings, heating gas and preventing it from cooling to form new stars. This feedback can alter the flow of matter along filaments and affect the evolution of nearby structures. Similarly, supernovae within galaxies can drive powerful winds that eject gas and metals into intergalactic space. This enriched material can then flow along filaments to other galaxies, influencing their chemical composition and star formation. The cosmic web thus serves not only as a highway for galaxy movement, but also as a channel for the exchange of materials between galaxies. The flow of galaxies along the cosmic web is not uniform, but varies with cosmic time. In the early universe, the web was more densely packed, and galaxies moved along its filaments more rapidly. As the universe expands, the web stretches, and the flow of galaxies slows. Eventually, as dark energy accelerates the expansion of the universe, distant filaments will move beyond each other's gravitational influence, and the flow of galaxies between them will cease. This cosmic choreography galaxies, flowing along invisible threads of dark matter shapes, the architecture of the universe we observe. It determines where galaxies form, how they evolve, and how they cluster together. The cosmic web is not just a static backdrop, but a dynamic environment that guides the journey of every galaxy, including our own. As we contemplate our place within this vast cosmic network, we realize that our galaxy is not an isolated island, but part of an interconnected system spanning billions of light-years. The Milky Way, like all galaxies, follows the threads of the cosmic web, its path shaped by forces acting across cosmic distances and timescales. The journey of galaxies along the cosmic web reminds us of the dynamic nature of our universe. What appears static on human timescales is, on cosmic timescales, a fluid dance galaxies flowing along invisible currents, clusters growing as they accrete new members, and the web itself stretching as the universe expands. We are witnessing just one moment in this ongoing cosmic ballet, a snapshot of a universe in constant motion and evolution. In our next chapter, we'll explore the vast empty spaces between the filaments, the cosmic voids that make up most of the volume of our universe. These voids are not merely empty spaces, but integral components of the cosmic web, shaping the distribution of galaxies and the flow of matter throughout the cosmos. For now, imagine the silent journey of billions of galaxies, each following its path along the invisible threads that connect every point in our vast universe. Empty spaces speak louder than words in the grand cosmic narrative. While we focused on the luminous galaxies and the dark filaments that connect them, now we turn our gaze to what lies between the vast cosmic voids that dominate the volume of our universe. These immense bubbles of near emptiness are not merely the absence of structure, but are fundamental to understanding the cosmic web itself. Cosmic voids are the universe's most overlooked features, enormous regions spanning tens to hundreds of millions of light-years where galaxies are remarkably scarce. Though they appear as nothing, these voids comprise nearly 80% of the universe's volume, making them the dominant spatial feature of our cosmos. They are not truly empty, but contain only a handful of lonely galaxies drifting through their immense expanse. The largest known void, the Boötes void, stretches across an almost incomprehensible 330 million light-years. Discovered in 1981, this Great Nothing, as some astronomers call it, contains so few galaxies that if our Milky Way were positioned at its center, we wouldn't have discovered other galaxies until the 1960s. For perspective, light itself, the fastest thing in the universe, would take 330 million years to cross this single void. When we map the universe on its largest scales, these voids appear as enormous bubbles pressed against each other, separated by the filaments and sheets of the cosmic web. This structure resembles a cosmic foam, with galaxies tracing the edges of bubbles, while the interiors remain largely devoid of visible matter. This pattern emerges naturally from the physics of cosmic evolution, as matter flows away from less dense regions toward denser ones. What makes these voids so fascinating is not just their size, but their role in cosmic structure formation. They are not passive features, but active participants in the evolution of the cosmic web. As the universe expands, voids grow larger and emptier, pushing galaxies along their edges into filaments and clusters. This process, called void expansion, contributes significantly to the movement of galaxies along the cosmic web. Think of voids as cosmic sculptures, defined as much by what they push away as by what they contain. They expand faster than the general cosmic expansion, continually evacuating matter from their interiors and pushing it toward their boundaries. This outward pressure, combined with the gravitational pull of filaments, guides galaxies along preferred paths, reinforcing the structure of the cosmic web. The boundaries between voids, where they press against each other, form the sheets and filaments of the cosmic web. Galaxies caught in these boundary regions experience complex forces pushed from behind by expanding voids and pulled forward by the gravity of filaments and clusters. This combination of push and pull is like a cosmic conveyor belt, transporting galaxies along predetermined routes through the universe. Surprisingly, voids are not completely empty. The rare galaxies found within voids are fundamentally different from those in denser environments. Void galaxies tend to be smaller, bluer, and more actively forming stars. Isolated from the processes that strip gas and halt star formation in cluster galaxies, these void dwellers continue peaceful evolution, slowly converting gas into stars without the disruptive influences experienced by their counterparts in denser regions. These void galaxies offer a unique laboratory for studying galaxy evolution in isolation, free from environmental effects. Their properties suggest that many of the changes galaxies undergo, transitioning from spiral to elliptical shapes, from blue to red colors, from active to passive star formation, are driven primarily by environment rather than internal processes. In the emptiness of voids, galaxies follow a different evolutionary path. The emptiness of voids presents a challenge to our understanding of galaxy formation. Standard models predict more galaxies in voids than we observe, a discrepancy that has led to new theories about how galaxies form and evolve. Some researchers suggest that the harsh radiation environment of voids inhibits gas cooling and star formation. Others propose that void galaxies form later or grow more slowly than their counterparts in denser regions. What makes voids particularly valuable to cosmologists is their simplicity. While dense regions of the cosmic web have undergone complex, nonlinear evolution, voids remain closer to their initial conditions. This makes them excellent probes of fundamental physics, from the nature of dark energy to modifications of Einstein's theory of gravity. By studying how voids expand and evolve, astronomers can test competing cosmological models with fewer complicating factors. The distribution and properties of voids also provide crucial constraints on cosmological parameters. The number, size, and shapes of voids depend sensitively on the amount and nature of dark matter and dark energy in the universe. By cataloging thousands of voids and analyzing their statistics, astronomers can independently measure these fundamental parameters and cross-check results from other methods. The boundaries of voids, where they meet the cosmic web, are particularly interesting regions. These void boundaries, or walls, contain galaxies caught in the transition between the emptiness of voids and the density of filaments. Studies of these boundary regions reveal how galaxies are processed as they flow from voids into the cosmic web proper. How their gas content, star formation rates, and morphologies begin to change as they encounter denser environments. Voids also affect how light travels across the universe. As light from distant galaxies passes through voids, it experiences slight gravitational effects that can be measured statistically. This phenomenon, called the integrated Sachs-Wolf effect, causes photons to gain or lose energy as they traverse the changing gravitational potentials of expanding voids. By correlating galaxies with subtle temperature variations in the cosmic microwave background radiation, astronomers have detected this effect, providing direct evidence for dark energy's influence on cosmic structure. The evolution of voids over cosmic time tells a story of growing emptiness. In the early universe, density contrasts were smaller and voids were less pronounced. As the universe expanded, gravitational forces amplified these initial differences. Dense regions grew denser, while underdense regions became emptier. Today's voids represent the culmination of this process, regions where matter has been steadily evacuated over billions of years. Future surveys like those planned for the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will map voids with unprecedented precision, allowing astronomers to track their evolution across cosmic time. These observations will reveal not just the current state of voids, but their entire developmental history, providing new insights into the forces that shape cosmic structure. One particularly fascinating aspect of voids is their role in the cosmic velocity field. Galaxies near void boundaries experience strong outward-directed forces, creating a distinct velocity signature that can be measured in large galaxy surveys. These void outflows contribute significantly to the overall movement of galaxies through the cosmos and help shape the large-scale distribution of matter. The interplay between voids and filaments creates a cosmic ecosystem where matter circulates according to gravitational forces. Gas flows out of voids, along sheets, into filaments, and eventually into clusters, a cosmic circulation pattern driven by gravity's inexorable pull. This flow determines where galaxies form, how they evolve, and how they cluster together on the largest scales. What might it be like to travel through a cosmic void? An interstellar traveler crossing a void would witness an increasingly empty sky. The familiar tapestry of galaxies would thin out until only a sparse scattering remained, most concentrated in a ring-like structure around the void's periphery. The vast emptiness would be interrupted only occasionally by isolated galaxious cosmic hermits that formed in relative isolation. For any hypothetical civilizations evolving on planets orbiting stars in void galaxies, the universe would appear starkly different from our own view. Their night sky would contain far fewer visible galaxies. Their cosmological models might develop differently, based on observations of a seemingly emptier universe. They might even conclude that they occupy a special, central position in the cosmos, a natural but incorrect inference from their unusual vantage point. The paradox of voids is that emptiness itself becomes a defining feature of cosmic structure. Just as musicians know that the spaces between notes are as important as the notes themselves, cosmologists recognize that voids are not merely the absence of structure, but are fundamental components of the cosmic web. They define the boundaries of filaments, influence the movement of galaxies, and dominate the volume of the observable universe. As we continue our journey through the cosmic web, remember that the vast emptiness between the luminous filaments is not a featureless void, but a dynamic and essential component of cosmic structure. The universe is defined as much by where matter isn't as by where it is. In the great cosmic symphony, the silences between notes are what give structure and meaning to the composition. The emptiness that surrounds the cosmic web is not a backdrop, but an active participant in the unfolding drama of cosmic evolution. And, as we'll see in our next chapter, discovering this intricate structure required not just powerful telescopes, but creative methods for mapping the invisible across billions of light years. The revelation of the cosmic web ranks among astronomy's greatest detective stories. For centuries, humans gazed at the night sky, believing the stars existed in a relatively uniform distribution throughout space. The discovery that galaxies arrange themselves in a vast, interconnected pattern stretching across billions of light years required technological breakthroughs, scientific ingenuity, and a fundamental shift in our cosmic perspective. Our story begins in the 1780s with the observations of William Herschel, who first suggested that stars were not distributed randomly, but formed a vast, disk-like system, what we now call the Milky Way galaxy. Yet the true scale and structure of the universe remained hidden until the early 20th century, when Edwin Hubble proved that the mysterious spiral nebulae, visible through telescopes, were actually distant galaxies far beyond our own island universes containing billions of stars. This revelation expanded our cosmic horizon dramatically, but the distribution of these galaxies still appeared largely random. The first hint that something more organized might exist came in the 1930s, when Harlow Shapley and Adelaide Ames published their catalogue of galaxies. The data seemed to show some galaxies clustering together, but the sample was too small to reveal larger patterns. The breakthrough came in the 1970s and 1980s, with the pioneering work of astronomers like Vera Rubin, whose observations of galaxy rotations provided the first strong evidence for dark matter, and the team of Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. Geller and Huchra embarked on an ambitious project, mapping the three-dimensional positions of thousands of galaxies by measuring not just their locations in the sky, but also their distances from Earth. Distance measurement was the key innovation. By measuring the redshift of galaxies, how much their light is stretched toward the red end of the spectrum by cosmic expansion, astronomers could determine how far away these galaxies were. This added the crucial third dimension needed to reveal the true structure of the universe. In 1986, Geller and Huchra unveiled their Slice of the Universe, a wedge-shaped survey showing the distribution of galaxies within a narrow slice of the sky, extending outward for hundreds of millions of light-years. What they found astonished the astronomical community. Rather than being randomly distributed, galaxies formed a distinct pattern of clusters, filaments, and voids, a cosmic web. Most dramatic was their discovery of the Great Wall, a sheet-like structure of galaxies stretching across more than 500 million light-years. This immense feature, which would take light itself 500 million years to cross, was the first identified large-scale structure in the universe. Its discovery challenged existing theories about how structure forms and evolves in the cosmos. Around the same time, other surveys were revealing equally surprising structures. The Boötes Voidan, enormous region, nearly devoid of galaxies, was discovered in 1981 by Robert Kirshner and his team. With a diameter of roughly 330 million light-years, this supervoid highlighted the contrast between the densely populated filaments and the emptiness between them. These early discoveries were made with relatively modest equipment and sample sizes by today's standards. Astronomers were mapping perhaps tens of thousands of galaxies, impressive, but still only a tiny fraction of the observable universe. The true breakthrough would come with the advent of large-scale digital sky surveys that could observe and catalogue millions of galaxies automatically. The first of these new generation surveys was the 2-degree field galaxy redshift survey, TWAD-FGRS, which began in 1997 using the Anglo-Australian telescope. This groundbreaking project measured the redshifts of over 220 galaxies, creating a three-dimensional map that clearly showed the cosmic web extending across billions of light-years. But the most comprehensive picture came from the Sloan Digital Sky Survey, SDSS, which began observations in 2000 and continues in different phases today. Using a dedicated 2.5-meter telescope equipped with a 120-megapixel camera and spectrographs capable of measuring hundreds of galaxy redshifts simultaneously, SDSS has produced the most detailed maps of the large-scale structure of the universe ever created. The SDSS revealed structures even larger than the Great Wall. The Sloan Great Wall, discovered in 2003, extends for approximately 1.5 billion light-years, making it one of the largest known structures in the universe. These observations confirmed that the cosmic web was not a statistical fluke, but a fundamental feature of cosmic structure extending across the observable universe. What made these discoveries possible was not just technological advancement, but creative approaches to visualization and analysis. Converting millions of galaxy positions into comprehensible maps required new techniques. Astronomers developed methods like the Friends of Friends algorithm, which identifies clusters by connecting galaxies that are closer to each other than a specified distance, and void-finding algorithms that identify the empty regions between filaments. Three-dimensional visualization proved particularly challenging. Early maps used simple plots with each galaxy represented by a point, but these became cluttered and difficult to interpret as sample sizes grew. More sophisticated techniques emerged, including density maps that highlight the filamentary structure and slices through the 3D distribution that reveal the web-like pattern more clearly. Computer simulations played a crucial role in understanding these observations. In the 1980s, pioneering computational cosmologists like Simon White, Mark Davis, George Efstathiou, and Carlos Frenk ran simulations showing how dark matter would collapse under gravity to form a web-like structure. The striking similarity between these simulations and the observed galaxy distribution provided strong evidence that galaxies trace an underlying dark matter web. The discovery of the cosmic web wasn't just about mapping galaxies, but required multiple lines of evidence coming together. X-ray observations revealed hot gas concentrated in galaxy clusters, while gravitational lensing, the bending of light by gravity, allowed astronomers to map dark matter directly. These complementary approaches confirmed that the web-like structure extended to all forms of matter, not just visible galaxies. Weak gravitational lensing has been particularly valuable in confirming the existence of dark matter filaments. By carefully measuring the slight distortions in the shapes of background galaxies, astronomers can detect the gravitational influence of dark matter lying between us and these distant light sources. These observations have directly revealed dark matter filaments connecting galaxy clusters, confirming that the cosmic web isn't just a pattern of visible galaxies, but reflects a deeper structure in the underlying dark matter. Radio astronomy has added another dimension to our understanding of the cosmic web. Giant radio telescopes like the Very Large Array and the upcoming Square Kilometre Array can detect the faint radio emissions from gas in filaments. These observations provide evidence for the warm-hot intergalactic medium, WHIM diffuse gas, that permeates the cosmic web and may contain up to half of all the ordinary matter in the universe. The discovery of the cosmic web represents a perfect example of how science progresses through the interplay of observation, theory, and technology. Theoretical physicists had predicted that gravity would create a web-like structure in the universe, but confirming this required increasingly sophisticated observations. Each new survey, with better instruments and larger sample sizes, revealed the web in greater detail and on larger scales. Today, our maps of the cosmic web extend across billions of light-years and include millions of galaxies. Projects like the Dark Energy Survey, the Extended Baryon Oscillation Spectroscopic Survey, EBOS, and the upcoming Vera-C, Rubin Observatory Legacy Survey of Space and Time, LSST, continue to map the universe in ever greater detail, pushing our understanding to larger scales and earlier cosmic times. What's particularly remarkable about the discovery of the cosmic web is how it overturned our intuitive understanding of the universe. Rather than being uniformly distributed or arranged in simple clusters, galaxies form an intricate, interconnected pattern that defies easy classification. The universe has a complex geometry that emerges from the interplay of gravity, dark matter, and cosmic expansion. This discovery has profound philosophical implications. The cosmic web demonstrates how complex structures can emerge naturally from simple physical laws acting over cosmic time. From tiny quantum fluctuations in the early universe, amplified by inflation and developed through gravitational attraction, arises a vast cosmic architecture of breathtaking complexity and beauty. The journey from seeing stars as random points of light to recognizing the vast, interconnected web they form represents one of humanity's greatest intellectual achievements. It required not just technological innovation, but conceptual leaps, the ability to visualize structures too vast to see directly, and to connect observations across enormous scales of space and time. As we continue mapping the cosmic web, each new survey reveals additional details and extends our view to larger scales and earlier cosmic times. The upcoming Euclid Space Telescope and the Nancy Grace Roman Space Telescope will map dark matter directly through gravitational lensing, revealing the cosmic web in unprecedented detail. The James Webb Space Telescope peers deep into the universe's history, showing how the web assembled in the early cosmos. What began with simple observations of galaxy clusters has evolved into a comprehensive understanding of the largest structure in existence, a network spanning billions of light years, encompassing trillions of galaxies, and shaped by forces acting across the entire history of the universe. From our tiny planet, human minds have mapped the cosmic web, an achievement that stands as a testament to our species' curiosity and ingenuity in understanding our place in the cosmos. As we look up at the night sky, we now know that the seemingly random scattering of stars and galaxies actually traces an immense paterna cosmic web whose full extent stretches far beyond what our eyes can see, but whose structure our minds have nonetheless come to comprehend. Gravity stands as the universe's master weaver. While we marvel at the immense cosmic web stretching across billions of light years, connecting distant galaxies through invisible threads, we must recognize the force responsible for this grandeur. Gravity, the weakest, yet most far-reaching of nature's fundamental forces, shapes the largest structures in existence through its patient, persistent pull across cosmic time. When Isaac Newton watched an apple fall in the 17th century, he recognized a profound connection. The same force pulling the apple toward Earth also keeps the moon in orbit and guides planets around the sun. Einstein later revealed gravity's deeper nature not as a force acting across distance, but as a curvature of space-time itself. These insights laid the foundation for understanding gravity's role in weaving the cosmic web. Gravity's extraordinary reach makes it uniquely qualified to shape cosmic structure. While the strong and weak nuclear forces operate only at subatomic distances, and electromagnetic forces are effectively neutralized on large scales by the balance of positive and negative charges, gravity feels no such constraints. It reaches across the entire observable universe, gradually pulling matter toward matter over billions of years. The cosmic web emerges from gravity's cumulative influence, acting on tiny initial density variations. In the aftermath of the Big Bang, the universe was remarkably uniform, with density differences of merely 1 part in 100, 0. These slight irregularities, quantum fluctuations stretched to cosmic scales during inflation, provided the seeds from which all structure would grow. Regions with slightly more matter exerted slightly stronger gravitational pulls on their surroundings. This additional attraction caused these denser regions to grow denser still, while areas with less matter gradually emptied as their contents were drawn away. Over cosmic time, this process amplified the initial tiny variations into the dramatic contrasts we observe today, the dense filaments and clusters separated by vast, nearly empty voids. What makes gravity particularly effective at building cosmic structure is its cumulative nature. Unlike other forces that can repel as well as attract, gravity only pulls. As matter begins to concentrate in a region, its growing mass increases its gravitational influence, attracting still more matter. This positive feedback loop, what astronomers call gravitational instability, transforms small initial advantages into the enormous structures of today's cosmic web. The timescale of this process is truly cosmic. The filaments and clusters we observe today have been shaped by gravity acting over billions of years. Even with its relentless pull, gravity works slowly on such vast scales. A typical galaxy moving along a filament might travel at several hundred kilometers per second, incredibly fast by human standards, but requiring millions or billions of years to traverse significant cosmic distances. Gravity's influence extends beyond simply pulling matter together. It creates a complex gravitational landscape across the universe's regions of higher and lower gravitational potential that guide the flow of matter along preferred paths. Matter tends to flow from regions of higher gravitational potential voids to lower potential filaments and clusters, following the path of least resistance through this gravitational topography. This gravitational landscape can be visualized as a vast, undulating surface with peaks representing voids and valleys representing clusters. Matter flows downhill in this landscape, gathering in the deepest valleys and ridges. The resulting flow patterns naturally create the filamentary structure we observe, matter streaming along the lowest paths connecting gravitational wells. The interplay between gravity and cosmic expansion creates the tension that shapes the web. While gravity pulls matter together, the universe's expansion works to drive it apart. On small scales, gravity overwhelms expansion, allowing galaxies and clusters to form and remain bound. On the largest scales, expansion dominates, stretching the cosmic web as the universe grows. At intermediate scales, the filaments of the cosmic web, we see a dynamic balance between these competing influences. Individual galaxies experience this gravitational web through what astronomers call tidal forces, the difference in gravitational pull across an object. Just as the Moon creates tides on Earth by pulling more strongly on the near side than the far side, the cosmic web exerts tidal forces on galaxies, stretching them along the direction of filaments. This tidal stretching helps align galaxies with the filaments they inhabit, creating the observed correlation between galaxy orientation and the cosmic web. Galaxy clusters, sitting at the nodes where multiple filaments meet, serve as the strongest gravitational anchors of the cosmic web. These massive structures, containing thousands of galaxies and enormous amounts of dark matter, create deep gravitational wells that dominate their surroundings. Matter flows toward these wells along the connecting filaments, drawn by their irresistible gravitational pull. The gravitational influence of these clusters extends far beyond their visible boundaries. The Laniakea supercluster, our home in the cosmic web, spans more than 500 million light-years and contains over 100 galaxies, all moving together under the influence of a shared gravitational center. Even our Milky Way, located in a relatively quiet cosmic suburb, experiences this pull, moving at several hundred kilometers per second toward the center of Laniakea. Perhaps most striking is how gravity creates order from chaos. The early universe was nearly uniform, with matter distributed almost evenly throughout space. Through gravity's influence, this uniformity evolved into the complex, hierarchical structure we observe today: cosmic web with clusters, filaments, sheets, and voids arranged in a pattern that emerges naturally from gravitational processes. This emergent order reflects a fundamental principle in physics. Systems under the influence of long-range attractive forces naturally develop complex structures. We see similar patterns in other systems governed by attractive forces, from the branching patterns of lightning to the formation of snowflakes. The cosmic web represents this principle operating on the grandest possible scale. Gravity's role extends beyond shaping the distribution of matter to influencing the properties of the galaxies themselves. A galaxy's location within the cosmic web, whether in a dense cluster, along a filament, or in a relatively isolated region, determines the gravitational environment it experiences, affecting its evolution and characteristics. Galaxies in clusters experience frequent gravitational interactions with neighbors, leading to mergers, tidal disruptions, and transformations from spiral to elliptical shapes. Those along filaments receive a steady flow of gas guided by the filament's gravitational channel, fueling star formation. Isolated galaxies in voids evolve more slowly and peacefully, shaped primarily by internal processes, rather than external gravitational influences. Even the impressive speed at which galaxies move hundreds or thousands of kilometers per secondis, a direct consequence of gravity's cumulative pull across vast distances and times. These velocities represent the conversion of gravitational potential energy into kinetic energy as matter falls toward dense regions. The fastest galaxies are typically those that have fallen furthest through the gravitational landscape, accelerated by the combined pull of all surrounding matter. The most dramatic manifestation of gravity's influence appears in galaxy clusters, where thousands of galaxies orbit a common center at speeds approaching thousands of kilometers per second. These enormous speeds reflect the immense gravitational wells created by clusters, which contain not just the visible galaxies, but vastly more dark matter and hot gas. The rapid orbital motion of cluster galaxies provided some of the first evidence for dark matter, as the visible mass alone was insufficient to explain such high velocities. Galaxy clusters also reveal gravity's influence through gravitational lensing, the bending of light around massive objects. Images of distant galaxies can be stretched, duplicated, or formed into arcs and rings as their light passes through the curved spacetime around clusters. These lensing effects allow astronomers to map the total mass distribution within clusters, confirming that dark matter follows the same filamentary structure as visible matter. On the largest scales, gravity plays a cosmic tug-of-war, with dark energy the mysterious force accelerating the universe's expansion. While gravity works to pull matter together, dark energy pushes space itself apart. In the early universe, matter was dense enough for gravity to dominate, allowing the cosmic web to form. But as the universe expands and matter dilutes, dark energy gains the upper hand, eventually preventing gravity from forming structures larger than those we observe today. This competition between gravity and expansion creates a natural limit to the size of cosmic structures. The largest filaments and superclusters we observe represent the maximum size that gravity could assemble before cosmic expansion became too rapid. Current observations suggest this maximum scale is roughly 1 billion light-years, coinciding with the size of the largest observed structures like the Sloan Great Wall. For all its cosmic importance, gravity remains the least understood of the fundamental forces. While we can describe its effects precisely using Einstein's general relativity, we have yet to reconcile gravity with quantum mechanics or fully understand how it relates to the other fundamental forces. The cosmic web itself may offer clues, as its structure preserves information about gravity's behavior across cosmic history. Despite these mysteries, one thing remains clear: gravity's patient pull across billions of years has transformed the nearly uniform early universe into the rich cosmic tapestry we observe today. From the smallest planetary systems to the largest superclusters, gravity shapes structure across all cosmic scales, creating a hierarchy of organization from simplicity to complexity. As we continue our journey through the cosmic web, remember that each filament, each galaxy, each cluster represents gravity's handiwork, the result of a fundamental force acting across vast spans of time and space. The invisible thread connecting every galaxy is not metaphorical but physical, the gravitational relationship that binds all matter in a single, interconnected cosmic dance. In our next chapter, we'll explore how ordinary matter, the gas, dust, and stars that make up the visible universe, traces and flows along this gravitational framework, forming the luminous markers of the cosmic web that our telescopes can detect. Between the glittering galaxies that trace the cosmic web flows something unseen yet fundamental, an ethereal ocean of gas spanning the vast gulfs between stars and galaxies. This diffuse matter, though nearly invisible to our telescopes, plays a crucial role in the cosmic drama, flowing along dark matter filaments and fueling the formation and evolution of every luminous object in the night sky. The cosmic web consists of more than just galaxies and dark matter. Ordinary matter, the protons, neutrons, and electrons that make up everything familiar to us, exists not only in stars and galaxies, but also in the seemingly empty space between them. This intergalactic medium is not truly empty, but filled with extremely tenuous gas, primarily hydrogen and helium, with traces of heavier elements. What makes this gas so challenging to detect is its extreme diffuseness. In the vast voids between filaments, a typical cubic meter might contain just a few atoms, a vacuum more perfect than any we can create on Earth. Along the filaments, the density increases, but remains incredibly low by terrestrial standards. Yet despite its tenuousness, this gas constitutes a significant fraction of all ordinary matter in the universe. Most of this intergalactic gas exists in a state unlike anything found naturally on Earth, a plasma so hot that electrons have been stripped from their atoms, yet so diffuse that it barely radiates. Astronomers call this the warm-hot intergalactic medium, or WIM, with temperatures ranging from 100 to 10 million degrees Celsius. Despite these extreme temperatures, the gas doesn't glow brightly because of its incredibly low density. The WIM poses one of modern astronomy's most persistent puzzles. When astronomers take inventory of all visible matter in the universe, the stars, galaxies, dust, and cold gas, they find only about half of the ordinary matter that should exist according to measurements of the early universe. The rest has been dubbed the missing baryon problem, and most astronomers now believe these missing baryons reside in the WIM, hidden from most observational techniques. Finding this elusive gas requires ingenious methods. One approach uses quasars, extremely bright, distant objects powered by supermassive black holes as cosmic flashlights. As quasar light travels through the intergalactic medium, atoms in the gas absorb specific wavelengths, creating distinct fingerprints in the spectrum. By analyzing these absorption features, astronomers can map the distribution, temperature, and composition of gas along the line of sight. These observations reveal that intergalactic gas is not distributed randomly but follows the same filamentary structure as galaxies and dark matter. The densest, hottest gas concentrates along the dark matter filaments, tracing the cosmic web just as galaxies do. This correlation confirms that all components of the universe, dark matter, galaxies, and intergalactic gas, flow along the same cosmic highways. What drives this correlation is gravity's influence on gas. Just as dark matter flows toward dense regions under gravity's pull, gas follows the same gravitational gradients. As gas falls into filaments, it experiences shock, heating the conversion of gravitational potential energy into thermal energy as the gas compresses and collides with itself. These shocks can heat the gas to millions of degrees, creating the hot plasma of the WIM. Recent observations with X-ray telescopes have directly detected some of this hot gas in the spaces between galaxies. In 2020, astronomers using the XMM Newton Space Telescope observed a filament of hot gas connecting two galaxy clusters, providing direct evidence of the WIM tracing cosmic filaments. Similar observations with the Rosetta X-ray telescope have mapped hot gas in nearby filaments, revealing the gaseous component of the cosmic web. The flow of gas along filaments creates cosmic rivers that feed galaxies and clusters. Just as rivers on Earth carry water from mountains to the sea, these cosmic rivers transport gas from the diffuse intergalactic medium into the dense environments where stars and galaxies form. This process, called cosmic accretion, provides the raw material for galaxy growth and evolution. Galaxy clusters, sitting at the nodes where multiple filaments meet, accumulate enormous amounts of hot gas. This intracluster medium, heated to tens of millions of degrees by gravitational compression, emits X-rays that astronomers can detect. X-ray observations reveal that this gas forms a diffuse halo, extending far beyond the visible galaxies, containing more mass than all the cluster's stars combined. The temperature and distribution of this cluster gas provide crucial information about the underlying dark matter. Since both gas and dark matter respond to the same gravitational forces, the hot gas traces the dark matter distribution. By mapping the properties of this gas, astronomers can infer the amount and distribution of invisible dark matter shaping the cluster. But the story of gas in the cosmic web isn't just about passive flow along gravitational channels. The relationship between galaxies and the intergalactic medium is dynamic and reciprocal. As gas flows into galaxies, it fuels star formation. These stars, particularly the most massive ones, eventually explode as supernovae, ejecting energy and heavy elements back into surrounding space. The most powerful cosmic feedback comes from supermassive black holes at galaxy centers. As these black holes consume matter, they can release enormous amounts of energy, driving outflows of hot gas that extend far beyond their host galaxies. These outflows enrich the intergalactic medium with heavy elements forged in stars and regulate the flow of gas along filaments, creating a cosmic ecosystem of gas circulation. This circulation of gas between galaxies and the intergalactic medium represents a cosmic recycling process that has operated throughout the universe's history. The first generation of stars formed from pristine hydrogen and helium. As these stars died, they enriched their surroundings with heavier elements like carbon, oxygen, and iron. This enriched material then flowed along filaments to form new generations of stars and planets, including, eventually, Earth and everything on it. The chemical composition of intergalactic gas provides a historical record of this enrichment process. Regions near galaxies contain higher concentrations of heavy elements, while more distant regions remain relatively pristine. By measuring these abundance patterns, astronomers can trace how metals have spread through the cosmic web over billions of years, carried by galactic outflows and intergalactic currents. Perhaps most remarkable is how the flow of gas along cosmic filaments creates a kind of cosmic metabolism. Gas flows in, fuels star formation, becomes enriched with heavy elements, and flows out again, only to be incorporated into new generations of stars and planets. This cycling of matter connects every galaxy to the broader cosmic web, making the universe a single, interconnected system. Recent observations suggest that even the Milky Way participates in this cosmic gas flow. Our galaxy sits within a filament of the local sheet, receiving a steady influx of gas that helps maintain our current rate of star formation. Without this cosmic sustenance, our galaxy would have exhausted its star-forming potential billions of years ago. Not all gas in the cosmic web is hot. Some filaments contain cooler gas, with temperatures of tens of thousands of degrees still hot by human standards, but cool enough to contain neutral hydrogen. This gas can be detected through its absorption of light from distant quasars, creating what astronomers call the Lyman alpha forest, a series of absorption lines in quasar spectra, each representing a cloud of neutral hydrogen along the line of sight. The Lyman alpha forest provides a detailed map of gas distribution throughout cosmic history. By observing quasars at different distances, astronomers can see how the intergalactic medium has evolved over billions of years. These observations reveal that the cosmic web was denser and more uniform in the past, gradually developing the pronounced filamentary structure we see today. Even colder gas exists in the cosmic web, particularly in the dense regions where filaments feed into galaxies. This cold gas, with temperatures of thousands rather than millions of degrees, can be detected through radio observations of neutral hydrogen. Massive radio telescopes like the forthcoming Square Kilometre Array will map this cold gas across cosmic scales, revealing how it flows from filaments into galaxies. The complex interplay between gas of different temperatures creates a multiphase medium within filaments. Hot, diffuse gas forms the outer layers, while denser, cooler gas concentrates along the central axis. This temperature structure influences how efficiently the gas can flow into galaxies and form stars, affecting the evolution of the cosmic web over time. Perhaps most intriguing are recent discoveries suggesting that magnetic fields permeate the cosmic web. These fields, though incredibly weak compared to those on Earth, may extend across millions of light years, roughly aligned with filaments. Their origin remains mysterious, perhaps seeded by the first stars and galaxies, and gradually amplified over cosmic time. These cosmic magnetic fields, detected through their effect on radio emissions from distant sources, may play a significant role in regulating gas flow along filaments. They can provide additional pressure support against gravity, influence the cooling and condensation of gas, and guide the propagation of cosmic ray-shy energy particles that traverse intergalactic space. The combination of magnetic fields, hot gas, and cosmic rays creates a complex, turbulent medium within filaments. This turbulence, chaotic, swirling motions spanning scales from thousands to millions of light years adds another layer of complexity to the cosmic web. It can both hinder and facilitate the flow of gas, creating eddies and vortices in the cosmic currents. Beyond hydrogen and helium, the intergalactic medium contains traces of heavier elements, a cosmic census of all star formation throughout history. Oxygen, carbon, silicon, and iron atoms, forged in stellar furnaces and expelled in supernovae explosions, travel vast distances along filaments. By measuring their abundance, astronomers can track how effectively galaxies have enriched their surroundings over cosmic time. The flow of these elements is not uniform but follows patterns dictated by the underlying cosmic web. Galaxy clusters, with their deep gravitational wells, tend to retain metals more effectively than less massive structures. Voids remain relatively pristine, containing gas closer to the primordial composition of the early universe. These differences create a cosmic geography of chemical enrichment that traces the flow of matter along filaments. Recent observations with the Hubble Space Telescope and large ground-based observatories have directly imaged some of the gas filaments connecting galaxies. Using specialized filters and incredibly long exposure times, astronomers have detected the faint emission from hydrogen gas illuminated by nearby galaxies or the general cosmic ultraviolet background. These observations provide direct visual evidence of the gaseous component of the cosmic web. What emerges from all these observations is a picture of the cosmic web as not merely a structural framework, but a dynamic circulatory system. Gas flows along filaments, fuels galaxy formation, becomes enriched with heavy elements, and returns to the intergalactic medium through galactic outflows. This cosmic circulation has operated for billions of years, gradually processing the universe's original hydrogen and helium into the complex elements needed for planets and life. The study of gas in the cosmic web addresses one of the most fundamental questions in cosmology. Where is all the ordinary matter? The missing baryon problem, has persisted for decades, with census after census of visible matter coming up short compared to predictions from cosmic microwave background observations. The discovery that much of this missing matter resides in the WHIM difficult to detect, but permeating the cosmic web resolves this discrepancy and completes our inventory of the universe's contents. As we develop more sensitive instruments and techniques, our ability to map this invisible component of the cosmic web continues to improve. Future X-ray observatories like Athena will detect the faint emission from hot gas in filaments. Radio telescopes like the Square Kilometre Array will map neutral hydrogen across cosmic scales. And next-generation ultraviolet telescopes will trace the circulation of heavy elements throughout the intergalactic medium. These observations will reveal not just the current state of gas in the cosmic web, but its entire evolutionary history, how it has flowed, cooled, condensed, and circulated over billions of years. This cosmic chronicle is written in the distribution and properties of intergalactic gas, waiting to be read by those with the right tools and techniques. As we continue our journey through the cosmic web, remember that the seemingly empty spaces between galaxies are not empty at all, but filled with tenuous gas flowing along invisible currents. These cosmic rivers, though nearly imperceptible to our instruments, play a crucial role in the life cycle of galaxies and the evolution of the universe itself. They are the lifeblood of the cosmic web, circulating matter and energy through the largest structure in existence. In our next chapter, we'll explore what happens when galaxies meet at the crossroads of the cosmic web, the dramatic collisions and mergers that occur most frequently where filaments intersect, reshaping galaxies and accelerating the evolution of the universe's most densely populated regions. Silence shatters at the cosmic crossroads. Where the great filaments of the universe intersect, galaxies dance a gravitational tango, spanning billions of years, a slow-motion collision of titans that transforms everything in its path. These cosmic intersections, where multiple streams of the cosmic web converge, become the stages for the most dramatic events in galactic evolution. Galaxy collisions represent nature's grandest spectacles, interactions so vast they unfold over hundreds of millions of years, yet so violent they can transform spiral galaxies into amorphous ellipticals, trigger bursts of star formation visible across billions of light years, and feed supermassive black holes until they shine brighter than entire galaxies. And these epic encounters happen most frequently at the nodes where cosmic filaments meet. The cosmic web naturally concentrates galaxies at these intersections. Like cars converging at a highway junction, galaxies flow along filaments until they reach these cosmic crossroads. Here, the density of galaxies can be hundreds of times higher than average, creating environments where collisions become inevitable. What would be an extraordinarily rare event in cosmic voids or along isolated stretches of filaments becomes commonplace at these bustling intersections. When two galaxies approach each other, their mutual gravitational attraction accelerates their motion, drawing them into a complex orbital dance. Long before they physically intersect, their gravitational fields begin distorting each other's shapes. Spiral arms stretch and warp, and tidal tails of stars and gas extend outward, creating the striking bridge and tail structures visible in many interacting systems. The Antennae galaxies represent one of the most dramatic examples of this cosmic collision process. Located about 60 million light-years from Earth, this pair of merging galaxies has developed enormous tidal tails, extending more than 350 light-years, features that give the system its insect-like appearance. These tails formed as the galaxy's gravitational fields pulled stars and gas from each other during their initial pass. What makes these collisions particularly transformative is that galaxies are mostly empty space. The stars within galaxies are separated by such vast distances that direct stellar collisions are extraordinarily rare, even during galaxy mergers. Instead, it's the gas and dust that interact most dramatically, crashing together, compressing, and triggering the birth of new stars. When gas clouds from two galaxies collide, they compress to densities far higher than normally found in interstellar space. This compression triggers gravitational collapse within the clouds, leading to bursts of star formation orders of magnitude more intense than the steady rate seen in isolated galaxies. These starburst events can transform billions of solar masses of gas into new stars within just a few million years. The evidence of these starbursts appears as bright blue regions scattered throughout colliding galaxies, areas filled with massive, newly formed stars that burn hot and blue. These massive stars live fast and die young, many exploding as supernovae within just a few million years of their birth. Their brief, brilliant lives temporarily illuminate the chaos of the collision before they explode, enriching the surrounding gas with heavy elements. Perhaps most dramatic is how these collisions feed the supermassive black holes lurking at galaxy centers. As galaxies merge, their central black holes, each millions or billions of times more massive than our Sun, spiral toward each other. Meanwhile, the gravitational disruption of the collision sends enormous amounts of gas toward the galactic centers, providing fresh fuel for these cosmic monsters. When a supermassive black hole receives this influx of matter, it can transform into an active galactic nucleus, AGNA, object that outshines its entire host galaxy. The material, spiraling into the black hole, forms an accretion disk heated to millions of degrees, radiating intensely across the electromagnetic spectrum. The most powerful of these, called quasars, can be seen across billions of light years, making them among the most luminous objects in the universe. The relationship between galaxy mergers and supermassive black hole growth creates a cosmic feedback loop. As black holes consume infalling matter, they release enormous amounts of energy that can expel gas from the merging galaxies, temporarily halting both star formation and further black hole growth. This self-regulation process shapes the final properties of the merged galaxy and may explain why black hole masses correlate so tightly with the properties of their host galaxies. The ultimate fate of colliding galaxies depends on their relative sizes and the geometry of their encounter. When galaxies of similar mass collide head-on or in nearly circular orbits, they typically merge completely, their stars and gas mixing thoroughly. The result is usually an elliptical galaxia, rounded, somewhat featureless system with stars moving in random orbits rather than the organized rotation of a spiral galaxy. This transformation from spiral to elliptical explains a pattern astronomers observe in the cosmic web. Spiral galaxies dominate in lower density environments along filaments, while elliptical galaxies predominate in the dense cluster environments where filaments meet. This pattern reflects the collision history of these regions. Galaxies in dense clusters have typically experienced multiple mergers, transforming them from spirals to ellipticals. Not all collisions result in complete mergers. When a small galaxy encounters a much larger one, the smaller galaxy may be torn apart completely, its stars and gas absorbed by the larger galaxy, while its overall structure is destroyed. Our own Milky Way has experienced many such minor mergers, absorbing smaller satellites whose remnants can still be detected as streams of stars with similar properties moving together through our galaxy. The Sagittarius dwarf spheroidal galaxy represents an ongoing example of this process. This small galaxy is currently being torn apart as it orbits the Milky Way, leaving a stream of stars wrapping multiple times around our galaxy. Astronomers have identified dozens of similar streams from past accretion events, showing that our galaxy has grown significantly by consuming smaller neighbors. Even more dramatic is the impending collision between our Milky Way and the neighboring Andromeda galaxy. Currently separated by about 2.5 million light-years, these two spiral galaxies are moving toward each other at about 110 kilometers per second. In about 4.5 billion years, they will begin a series of close passes that will ultimately result in a complete merger, transforming the two spiral galaxies into a single massive elliptical. Computer simulations of this future collision show how the two galaxies will distort each other's shapes long before they physically intersect. Their spiral arms will stretch and warp, and long tidal tails will extend into intergalactic space. Stars currently in the Sun's neighborhood, including possibly the Sun itself, will be flung into different orbits, potentially far from the galactic center. Despite the violence of these collisions on galactic scales, their impact on individual planetary systems remains surprisingly minimal. The vast distances between stars mean that direct stellar encounters are extremely rare even during galaxy mergers. Our solar system will likely survive the Milky Way Andromeda collision intact, though it will find itself in a completely different galactic environment. The most massive collision environments in the universe are galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. These clusters form where multiple filaments of the cosmic web converge, creating dense knots of galaxies, gas, and dark matter. Within these environments, galaxies experience not just isolated collisions, but a constant gravitational harassment from multiple neighbors. The Coma Cluster, located about 320 million light-years from Earth, exemplifies these dense environments. Containing over 10 catalogued galaxies and thousands more smaller systems, this massive cluster sits at the intersection of several major filaments. The cluster's central regions are dominated by enormous elliptical galaxies, the products of multiple mergers throughout cosmic history. When entire clusters collide, they create the most energetic events in the universe since the Big Bang. The Bullet Cluster, located about 3.7 billion light-years away, shows the aftermath of two massive clusters passing through each other at speeds of thousands of kilometers per second. The collision separated the cluster's gas from their dark matter, providing some of the strongest direct evidence for dark matter's existence. These cluster collisions accelerate particles to nearly the speed of light, generating enormous radio structures called relics and halos. These structures, spanning millions of light-years, trace the shock waves and turbulence generated as clusters collide. They represent the largest particle accelerators in the universe, far more powerful than anything humans could construct on Earth. The frequency of galaxy collisions has changed dramatically throughout cosmic history. In the early universe, galaxies were closer together, and mergers were much more common. As the universe expanded, the average distance between galaxies increased, reducing the collision rate. Today, galaxy mergers are relatively rare in most environments, though they remain common at the dense nodes of the cosmic web. This evolution in merger frequency helps explain the changing population of galaxies throughout cosmic history. The early universe contained a higher proportion of irregular and disturbed galaxy systems in the process of colliding and merging. As the universe aged and the merger rate declined, more galaxies were able to settle into the regular spiral patterns we commonly observe today. Yet even as the overall merger rate has declined, collisions remain concentrated at the crossroads of the cosmic web. The flow of galaxies along filaments ensures a steady supply of new arrivals at these intersections, maintaining high galaxy densities and collision rates, even as the broader universe continues to expand. One particularly fascinating aspect of galaxy collisions is their role in redistributing heavy elements throughout the cosmos. When massive stars form during collision-induced starbursts, they quickly synthesize heavy elements in their cores. Many then explode as supernovae, ejecting these elements into intergalactic space. The turbulence and outflows generated by collisions can spread these materials across millions of light-years. The most spectacular galactic collisions can be seen across most of the observable universe. Ultraluminous infrared galaxies, ULIRGs, represent systems in the midst of gas-rich mergers, where star formation has been accelerated to hundreds or even thousands of times the rate in our Milky Way. The energy from this frenzied star formation is absorbed by dust and re-radiated as infrared light, making these systems among the most luminous infrared sources in the universe. Equally dramatic are quasars-active galactic nuclei so bright they can outshine all the stars in their host galaxies combined. Many quasars are triggered by the gas inflows associated with major galaxy mergers. These objects were more common in the early universe, when both galaxy merger rates and gas content were higher. By studying distant quasars, astronomers can trace the history of galaxy collisions throughout cosmic time. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is revealing galaxy collisions in the very early universe, showing systems in the process of assembly just a few 100 million years after the Big Bang. These observations help astronomers understand how the first massive galaxies formed at the nodes of the early cosmic web. While most dramatic at cluster intersections, collisions occur throughout the cosmic web. Even in relatively isolated sections of filaments, galaxies occasionally encounter each other as they flow along these cosmic highways. The difference is primarily one of frequency. Collisions are commonplace at filament intersections, but relatively rare along their length. The concentration of collisions at cosmic crossroads creates a kind of environmental processing machine. Galaxies entering these dense regions experience rapid evolution through mergers, tidal interactions, and gas stripping. Those that survive this gauntlet emerge transformed typically as red, elliptical systems with little ongoing star formation, having consumed or lost most of their gas. This environmental processing explains the observed correlation between galaxy properties and their position within the cosmic web. Bluer, star-forming spiral galaxies dominate in the lower density environments along filaments. Redder, more passive elliptical galaxies predominate in the dense cluster environments where filaments meet. This pattern reflects not just where galaxies formed initially, but how their environment has shaped their evolution. The collision environments at cosmic crossroads also influence the intergalactic medium surrounding them. The combined effect of supernovae, active galactic nuclei, and merger-induced outflows can expel enormous amounts of hot, metal-enriched gas into intergalactic space. This material can spread along filaments, enriching regions far from its origin and influencing future generations of galaxy formation. Perhaps most fundamentally, galaxy collisions at filament intersections represent the universe's primary mechanism for building larger structures. The hierarchical growth of galaxy-small systems merging to form larger onesis, most efficient where the cosmic web concentrates galaxies. Without these crossroads and the collisions they facilitate, the universe would lack its most massive galaxies and clusters. As we observe these collision environments across cosmic history, we're watching the universe assemble its largest structures piece by piece. Early, gas-rich mergers built the cores of today's massive galaxies. Later, drier mergers added additional stars while triggering less dramatic changes. The result is a universe where the most massive galaxies sit precisely where we would expect at the bustling intersections of the cosmic web. For all their violence and transformation, galaxy collisions represent a fundamental creative force in cosmic evolution. They trigger the formation of new stars, redistribute heavy elements needed for planets and life, and build the massive galaxies that anchor the cosmic web. They represent not destruction, but transformation, the universe rearranging itself into ever more complex configurations. As we continue our journey through the cosmic web, remember that the majestic elliptical galaxies dominating cluster centers, with their populations of billions of stars, are monuments to countless collisions throughout cosmic history. Each represents the culmination of a process that began with the flow of galaxies along filaments, their inevitable encounters at cosmic crossroads, and the gradual assembly of something new from these cosmic collisions. The cosmic web stretches beyond our direct observationa structure, so vast that no single telescope can capture its entirety, so complex that no single observation can reveal its evolution across cosmic time. To truly understand this grandest of structures, scientists have created detailed cosmic simulations, digital universes, born in supercomputers, that allow us to witness the cosmic web's birth, growth, and future. These virtual cosmos represent one of humanity's most ambitious computational endeavors, mathematical models that track trillions of particles representing dark matter and billions of cells modeling gas physics across billions of simulated years. From humble beginnings on early mainframe computers to today's massive parallel systems with hundreds of thousands of processors, cosmological simulations have revolutionized our understanding of the cosmic web. The quest to simulate the cosmic web began in the 1970s, with simple models tracking a few thousand particles under the influence of gravity. Early pioneers like James Peebles, Simon White, and Mark Davis created rudimentary simulations that, despite their limitations, revealed the essential tendency of gravitational forces to create filamentary structures. These early efforts, though primitive by modern standards, demonstrated that computers could help unveil the invisible architecture of the universe. A breakthrough came in 1985 with the publication of results from what became known as the Davis, Efstathiou, Frank, and White simulation, the first to convincingly demonstrate that dark matter naturally forms a cosmic web under the influence of gravity. With just 768 particles, minuscule by today's standards, this landmark simulation showed filaments, nodes, and voids emerging from initial conditions resembling the early universe. The striking similarity between these simulated structures and observed galaxy distributions provided compelling evidence for dark matter's existence and role in shaping cosmic structure. Today's simulations operate on an entirely different scale. The Millennium simulation, completed in 2005, tracked over 10 billion particles representing dark matter. More recent projects like Illustris TNG and Eagle simulate not just dark matter, but also the complex physics of ordinary matter-gas cooling, star formation, supernova explosions, black hole growth, and more. These simulations create virtual universes so detailed they can be directly compared with astronomical observations across cosmic history. The basic principles underlying these simulations remain remarkably simple, even as their implementation grows increasingly sophisticated. At their core, cosmological simulations solve the equations of gravity and increasingly hydrodynamics for an enormous number of particles or fluid elements. Starting from initial conditions that match the very early universe, the simulation advances in small time steps, calculating the forces on each particle and updating its position and velocity. What makes this process computationally challenging is the sheer number of gravitational interactions. In principle, every particle influences every other particle in the simulation, creating an n-squared scaling problem. Doubling the number of particles quadruples the computational cost. Various mathematical tricks and approximations, such as the tree algorithm and particle mesh methods, make the calculations manageable, allowing simulations to scale to billions or even trillions of particles. The initial conditions for these simulations come from observations of the cosmic microwave background, the earliest light in the universe, dating from just 380 years after the Big Bang. This radiation shows tiny temperature fluctuations that correspond to slight variations in matter density in the early universe. By translating these observed fluctuations into a distribution of simulation particles, scientists ensure their virtual universes begin with conditions matching our own. Running a major cosmological simulation requires not just sophisticated algorithms but also enormous computational resources. The Millennium simulation, for instance, ran on a supercomputer with 512 processors working in parallel for more than a month. More recent simulations like Illustris TNG have utilized tens of thousands of processor cores running simultaneously for months, consuming millions of CPU hours and generating hundreds of terabytes of data. The results justify these extraordinary resources. As the simulation progresses from its uniform initial state, gravity gradually amplifies the tiny initial density variations. Dark matter begins flowing from less dense regions toward denser ones. Over billions of simulated years, this flow creates a complex network of filaments, sheets, and nodessa, cosmic web, emerging naturally from simple gravitational physics, applied to initial conditions, matching the early universe. What makes these simulations particularly valuable is their ability to show the evolution of cosmic structure across time. Unlike astronomical observations, which provide snapshots of different regions at different cosmic epochs, simulations allow scientists to watch the same structures evolve continuously. A single simulation can show how the cosmic web assembled from the nearly uniform early universe to the complex structures we observe today. The largest dark matter simulations, like the Millennium XXL and Uchu simulations, track trillions of particles across volumes, spanning billions of light years. At these scales, they capture the statistics of cosmic structure: how filaments connect, how voids are distributed, and how structure grows over time. These large-scale patterns can be directly compared with galaxy surveys, providing crucial tests of our cosmological models. More specialized simulations focus on smaller regions with greater detail, resolving the internal structure of dark matter halos where galaxies form. These zoom-in simulations can follow the complex merger histories of individual halos, showing how they gradually assemble through hierarchical clustering small halos, merging to form larger ones, which themselves merge into still larger structures. The dark matter halos that emerge in these simulations display a remarkable universality. Despite forming through complex, nonlinear processes, they develop density profiles that follow a consistent mathematical form across a wide range of masses. This NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who first described it, becomes steeper toward the center of the halo but never forms a sharp peak. This universal profile represents an emergent property, a simple pattern arising from complex dynamics. While early simulations modeled only dark matter, modern cosmological simulations incorporate the physics of ordinary matter, the gas that will form stars, galaxies, and eventually planets. This addition enormously increases the computational complexity, requiring models for gas cooling, star formation, supernova feedback, black hole growth, and more. But the payoff is the ability to produce virtual universes containing not just dark matter structures but visible galaxies that can be directly compared with observations. The Illustris project, completed in 2014, represented a major advance in this direction, creating a simulation that included both dark matter and baryonic physics in a volume 106.5 million light-years across. Its successor, Illustris TNG, expanded to multiple simulation volumes, the largest spanning 300 million light-years. These simulations track not just where galaxies form, but their internal properties, their shapes, colors, star formation rates, and more. Similar projects like EAGLE, Evolution and Assembly of Galaxies and Their Environments, SIMBA, and Horizon AGN take different approaches to modeling the physics of galaxy formation, allowing scientists to test how sensitive their results are to specific implementation details. Despite their differences, these simulations converge on a consistent picture of how galaxies form and evolve within the cosmic web. The visualization of these simulations presents its own challenges. The raw output consists of particle positions, velocities, and various physical properties, not exactly an intuitive representation for human understanding. Various techniques transform this raw data into visualizations that reveal the cosmic web's structure. Density maps show the concentration of dark matter across space. Velocity field visualizations reveal the flow of matter along filaments, and renderings of the simulated galaxies show how visible matter traces the underlying dark matter structure. Some of the most striking visualizations employ volume rendering techniques similar to those used in medical imaging, by assigning colors and transparencies based on density, temperature, or other properties. These visualizations create three-dimensional representations of the cosmic web that can be rotated and explored interactively. The resulting images and animations have not just scientific value but aesthetic appeal, revealing the cosmic web's intricate beauty. Identifying structural features within simulations requires sophisticated algorithms. Filament finding codes trace the spine-like structures connecting dense nodes. Void finding algorithms identify the underdense regions between filaments. Halo finders locate the bound clumps of dark matter where galaxies form. These automated tools allow quantitative analysis of the cosmic web's properties across enormous datasets too large for manual inspection. One particularly powerful approach identifies filaments using techniques borrowed from Morse theory, a branch of mathematics, dealing with the topology of surfaces. These methods locate critical points in the density field maxima, minima, and saddle points, and use them to trace the spine of filaments. The result is an explicit network representation of the cosmic web that can be analyzed statistically. These statistical analyses reveal the cosmic web's fundamental properties. Filaments typically span tens to hundreds of millions of light-years, connecting clusters across vast cosmic distances. Their thickness ranges from about 1 to 10 million light-years, with denser filaments generally being thinner. The densest filaments tend to connect the most massive clusters, forming a kind of cosmic superhighway system for the flow of matter. Voids show similarly consistent properties in simulations. They typically span 30 to 200 million light-years in diameter, with larger voids generally being less empty than smaller ones. Their shapes tend to be roughly spherical but can be significantly distorted where they press against neighboring voids. And they evolve distinctively over time, expanding faster than the general cosmic expansion, becoming emptier and more distinct as the universe ages. Perhaps most valuable is how simulations allow scientists to connect observable galaxies to the underlying dark matter distribution. By modeling both components simultaneously, simulations reveal how galaxies trace the cosmic web not randomly, but preferentially, along filaments and especially at the nodes where filaments intersect. The simulated relationship between galaxy properties and their position within the cosmic web can be directly compared with observations, providing crucial tests of our models. These comparisons have revealed both striking successes and remaining challenges. On large scales, simulations reproduce the observed distribution of galaxies with remarkable fidelity. The filamentary structure, the sizes and distributions of voids, and the clustering of galaxies all match observations within expected uncertainties. This agreement provides strong evidence that our basic cosmological model, with its dark matter, dark energy, and initial conditions from the cosmic microwave background, correctly describes the universe's large-scale structure. On smaller scales, challenges remain. Simulations tend to predict more small satellite galaxies around Milky Way-sized galaxies than we observe the so-called missing satellites problem. They also predict central dark matter densities in dwarf galaxies higher than observations suggest the core cusp problem. These discrepancies could indicate either limitations in our simulation methods or the need for modifications to our understanding of dark matter itself. Addressing these challenges requires ever more sophisticated simulations. Modern efforts incorporate increasingly detailed models for the physics of galaxy formation, how gas cools and forms stars, how supernovae and black holes inject energy back into surrounding gas, how galaxies interact with their environment, and more. These processes operate on scales far smaller than can be directly resolved in cosmological simulations, requiring subgrid models that capture their aggregate effects on resolvable scales. The justification for these subgrid models comes from smaller-scale simulations that directly resolve the relevant processes. Simulations of individual galaxies can track the formation of individual stars and the detailed structure of interstellar gas. Simulations of galaxy clusters can resolve the shock heating and turbulence in intracluster gas. And simulations of the circumgalactic medium, the gas surrounding Galaxy S, can resolve the flows that connect galaxies to the broader cosmic web. Together, these simulations across different scales form a hierarchy of models that capture the universe's structure from the largest cosmological scales down to the formation of individual stars and planets. This multi-scale approach acknowledges that the cosmic web's properties emerge from processes operating across an enormous range of scales, from quantum fluctuations in the early universe to galaxy-scale outflows and beyond. As computing power continues to increase, so does the ambition of cosmological simulations. Future projects aim to simulate larger volumes with higher resolution and more detailed physics. The ultimate goal is a simulation that captures the full observable universe, with sufficient resolution to model individual galaxy ASA, virtual cosmos indistinguishable from the real one in its statistical properties. Such a simulation would serve as a kind of cosmic laboratory, allowing scientists to test how different physical processes and initial conditions affect the resulting universe. By varying parameters like the dark matter and dark energy content, the amplitude of initial fluctuations, or the details of galaxy formation physics, scientists can see how these changes propagate through cosmic history to affect the observable universe. These virtual universes also provide a crucial link between theory and observation. When astronomers discover unexpected features in galaxy surveys or cosmic microwave background measurements, simulations can help determine whether these features are consistent with our current understanding or require new physics. Similarly, when theorists propose modifications to our cosmological model, simulations can predict the observable consequences of these changes. Perhaps most promising is the role of machine learning in analyzing cosmological simulations. The enormous datasets produced by modern simulations, often hundreds of terabytes or more, exceed what human scientists can analyze manually. Machine learning algorithms can identify patterns in these datasets, classify structures, and even predict the outcomes of simulations with different parameters, accelerating the scientific discovery process. Some researchers have begun using neural networks to predict the full three-dimensional distribution of dark matter from limited observational data like galaxy positions or gravitational lensing measurements. Trained on cosmological simulations, these networks learn the relationship between observable properties and the underlying dark matter distribution, allowing more accurate reconstructions of the cosmic web from real astronomical data. The scientific impact of cosmological simulations extends far beyond the study of large-scale structure. By tracking the formation and evolution of galaxies within the cosmic web, these simulations help explain a wide range of astronomical observations, from the distribution of galaxy shapes and sizes to the chemical composition of stars and gas. They connect the visible universe we observe to the underlying physical processes that shaped it. These simulations also provide crucial context for understanding our own cosmic neighborhood, the Milky Way, and neighboring galaxies reside within a particular filament of the cosmic web, and their properties have been shaped by this environment. Simulations help us understand which aspects of our galactic home are typical and which might be unusual, placing our corner of the cosmos within the broader context of cosmic structure. Looking to the future, cosmological simulations will play a crucial role in extracting science from upcoming astronomical facilities. Projects like the Vera-C, Rubin Observatory, the Nancy Grace Roman Space Telescope, and the Square Kilometre Array will map the distribution of galaxies and matter with unprecedented precision. Interpreting these observations will require equally precise simulations that capture the relationship between observable properties and the underlying cosmic structure. The relationship between simulations and observations has become increasingly symbiotic. Observations inform the initial conditions and physical models used in simulations. Simulations, in turn, guide observational strategies and help interpret results. This back and forth between virtual and observed universes drives progress in cosmology, with each approach complementing and enhancing the other. Perhaps most profoundly, cosmological simulations allow us to witness cosmic history in a way no observation could provide. They show us the birth of the first structures in the early universe, their gradual assembly into the cosmic web, and even their potential fate in the distant future as dark energy drives an accelerating expansion. They allow us to see the universe not as a static entity, but as a dynamic, evolving system of cosmos with a history and a future. As we continue our journey through the cosmic web, remember that our understanding of this vast structure emerges not just from direct observation, but from the virtual universes created in supercomputers. These digital cosmos, though simplified approximations of the real universe, have revealed patterns and processes that would otherwise remain hidden from view. They allow us to see the invisible threads connecting galaxies across billions of light years, and to understand how these threads formed and evolved throughout cosmic history. In our next chapter, we'll explore a thought experiment. What if the cosmic web didn't exist? How would the universe differ, and what does this tell us about the web's essential role in cosmic evolution? By imagining a cosmos without structure, we gain a deeper appreciation for the web's fundamental importance to everything we observe, including, ultimately, our own existence. Cosmic absence beckons us to contemplate the unimaginable. What would our universe look like without its defining web of filaments, clusters, and voids? This thought experiment, imagining a cosmos without structure, reveals not just the web's physical significance, but its profound necessity for everything we know, including life itself. The cosmic web's absence would transform our universe into something unrecognizable. Without the clustering of matter into filaments and nodes, stars and galaxies as we know them would never form. The night sky would appear drastically different, perhaps even empty of the familiar points of light that have guided humanity since our earliest days. Life itself might be impossible in such a uniform cosmos. By exploring this counterfactual universe, we gain deeper insight into how crucial the cosmic web is for existence itself. To understand a universe without the cosmic web, we must first identify what fundamental changes would prevent its formation. The web emerges from tiny density fluctuations in the early universe, amplified by gravity over billions of years. Without these initial fluctuations, if the early universe were perfectly uniform, there would be no seeds from which structure could grow. Alternatively, without dark matter to amplify these seeds during the universe's youth, structure formation would be dramatically delayed or altered. Let's first imagine a universe without initial density fluctuations, a cosmos that begins in perfect uniformity. In the actual early universe, quantum processes during inflation created slight variations in density, about 1 part in 100, 0. These tiny differences provided the seeds from which all structure grew. In our hypothetical uniform universe, without these seeds, matter would remain evenly distributed throughout cosmic history. The most immediate consequence would be the absence of galaxies. Galaxies form when gas collapses within dark matter halos, which themselves form through the gravitational amplification of initial density fluctuations. Without these fluctuations, dark matter would remain uniformly distributed, never condensing into halos. Without halos, gas would lack the gravitational wells needed to collapse and form stars. The universe would remain a nearly homogeneous fog of hydrogen and helium. Stars themselves might still form in this uniform cosmos, but through vastly different mechanisms and at much later times. Without dark matter halos to facilitate gas collapse, star formation would require direct gravitational instability in the gas itself. This process would be exceedingly slow and inefficient, potentially delayed by trillions of years. When stars finally did form, they would appear sporadically throughout space, rather than clustered in galaxies. These isolated stars would differ dramatically from those we observe. Without the metal enrichment from previous generations of stars, they would consist almost entirely of hydrogen and helium. Their planets, if any formed, would lack the heavy elements needed for rocky worlds like Earth. The complex chemistry that enables life would be absent, replaced by a much simpler chemistry limited to the lightest elements. The universe's large-scale appearance would be strikingly different as well. Instead of the complex tapestry of filaments, clusters, and voids revealed by our galaxy surveys, we would see an almost uniform distribution of matter in all directions. No structures would extend across millions or billions of light years. No clusters would concentrate thousands of galaxies in relatively small volumes. The cosmic web's intricate geometry would be replaced by nearly perfect homogeneity. This uniformity would have profound consequences for cosmic evolution. In our universe, structure formation is hierarchical. Small structures form first, then merge to create larger ones. This process concentrates matter and energy, creating environments where complex physical processes can unfold. Without this concentration, the universe would remain in a perpetually simple state, lacking the environmental diversity needed for complex systems to evolve. The impact on potential life forms would be devastating. Without galaxies and their concentrated energy and matter, complex chemistry would struggle to emerge. Stars, if they formed at all, would be isolated, lacking the gravitational influence needed to create planetary systems with stable orbits. And without the heavy elements forged in stars and distributed through supernovae, the chemical building blocks of life, as we know it, would be absent. Even foundational observations that led to our current cosmological understanding would be impossible. In a universe without structure, Edwin Hubble would have found no galaxies whose redshifts could reveal cosmic expansion. Fritz Zwicky would have observed no galaxy clusters whose dynamics could suggest dark matter's existence. The entire empirical foundation of modern cosmology would be unavailable to potential observers within such a universe. Now let's consider a different scenario, a universe with initial density fluctuations, but without dark matter. In this cosmos, structure would still form, but through a dramatically different process and timeline. Without dark matter's gravitational influence, ordinary matter would remain coupled to radiation until the universe had cooled significantly, delaying the growth of structure by hundreds of millions of years. When structure finally began to form in this dark matter-free universe, it would follow a different pattern. Instead of the web-like network we observe, matter would collapse into simpler, more spherical structures. The intricate filaments, sheets, and voids of the cosmic web features that emerge specifically from dark matter's collisionless nature would be absent, replaced by a more uniform clustering. Galaxies in this alternative cosmos would differ dramatically from those we observe. Without dark matter halos to provide additional gravitational attraction, galaxies would be smaller, less stable, and likely to exhaust their star-forming gas more quickly. The majestic spiral patterns seen in galaxies like our Milky Way would be rare or absent, as these structures depend on the gravitational stability provided by dark matter. The timeline of cosmic evolution would be significantly extended. In our universe, the first stars formed just a few 100 million years after the Big Bang, within dark matter halos that had already begun assembling. Without dark matter, star formation would be delayed until ordinary matter alone could collapse under its own gravitia process, requiring much higher densities and thus much more time. The cosmic dark ages would stretch for billions rather than millions of years. These differences highlight dark matter's essential role in weaving the cosmic web. Though invisible to our telescopes, dark matter provides the gravitational scaffold upon which all visible structure forms. Its unique properties, interacting only through gravity, free from radiation, pressure, allow it to begin forming structures earlier than ordinary matter could alone. The cosmic web as we know it is, fundamentally, a dark matter phenomenon traced by the visible matter that later falls into its gravitational wells. Both of these counterfactual universes own, without initial fluctuations, another without dark matter share, a common feature. They would be far less efficient at concentrating energy and creating complexity. The cosmic web serves as a kind of universal infrastructure, channeling matter toward dense regions where stars and galaxies can form, energy can be processed, and complexity can emerge. Without this infrastructure, the universe would remain in a simpler, more diffuse state. This efficiency relates to another crucial aspect of the cosmic web, its role in breaking perfect symmetry. The early universe was remarkably uniform, with nearly the same temperature and density everywhere. Such perfect symmetry, while elegant, is also sterilely incapable of generating the complexity needed for rich cosmic evolution. The web's formation represents a cosmic symmetry breaking, creating distinct environments with different properties and evolutionary pathways. The contrast between high-density filaments and low-density voids creates cosmic gradients differences that can drive energy flows and complexity. Just as life on Earth depends on temperature and chemical gradients to drive metabolism and evolution, cosmic evolution depends on density and gravitational gradients to drive star formation, galactic evolution, and potentially the emergence of life. Without the cosmic web, these crucial gradients would be absent or significantly reduced. Consider how this relates to entropy's measure of disorder or randomness in a system. While the universe as a whole tends toward increasing entropy, the second law of thermodynamics, gravitational structure formation temporarily reverses this trend locally. By concentrating matter into filaments and clusters, gravity creates regions of lower entropy islands of order in an increasingly disordered cosmos. Without the web, this local entropy reduction would be greatly diminished, limiting the potential for complex structures to emerge. This perspective reveals the cosmic web as not merely a structural feature, but a fundamental process, the universe's primary mechanism for generating complexity through gravitational organization. The web represents the largest scale manifestation of this organizational principle, creating the conditions necessary for all smaller scale complexity, from galaxies to planets to potentially life itself. The implications extend to fundamental questions about cosmic habitability. In recent decades, scientists have recognized that many physical parameters seem finely tuned to allow for complex structures and potentially life. The cosmic web adds another layer to this consideration. Even with the right fundamental parameters, a universe without the web's organizational efficiency would likely remain sterile, lacking the concentrated energy flows and chemical complexity needed for life. Our existence, then, depends not just on the fundamental constants of nature, but on the structural organization those constants permit. The cosmic web, by efficiently concentrating matter and energy, creates the conditions necessary for stars, planets, and potentially life to form. Without this large-scale structure, even a universe with identical physical laws might remain forever simple, its matter too diffuse to generate complexity. These considerations highlight the deep connection between structure and complexity across all scales. From elementary particles organizing into atoms, atoms into molecules, molecules into cells, and ultimately into conscious beings capable of contemplating the cosmos. Each level of complexity depends on the structural organization of the level below it. The cosmic web sits at the foundation of this hierarchy, providing the large-scale organization upon which all smaller-scale structures depend. Recent research suggests this connection may be even deeper than previously recognized. Some scientists propose that gravity itself might be an emergent phenomenon, a fundamental force but a consequence of how information is organized in the universe. If true, this would further blur the distinction between physical laws and the structures they generate. The cosmic web would represent not just a consequence of gravity, but an integral part of how gravity itself operates on cosmic scales. Beyond these physical considerations lie philosophical implications. The cosmic web's necessity for our existence raises questions about cosmic purpose and meaning. Is the universe designed to generate complexity, or does complexity emerge naturally from simple physical laws operating over vast timescales? The web's formation from simple initial conditions through well-understood physical processes suggests the latter, demonstrating how extraordinary complexity can emerge without requiring extraordinary explanations. The web also challenges our intuitions about emptiness and substance. What appears empty to our direct perception, the vast spaces between galaxy sterns, out to be structured by invisible forces and filled with tenuous matter. The cosmic void is not truly void, but textured with meaning and causality. This realization echoes philosophical traditions that question the distinction between being and non-being, suggesting that emptiness itself has structure and significance. For astronomers and cosmologists, imagining a universe without the cosmic web serves as a powerful theoretical tool. By contrasting our universe with counterfactual alternatives, researchers can isolate the web's specific contributions to cosmic evolution. This approach has helped identify the crucial role of dark matter, the importance of initial density fluctuations, and the relationship between large-scale structure and galaxy formation. Computer simulations play an essential role in these explorations. By creating virtual universes with modified physics, different amounts of dark matter, altered initial conditions, or modified gravitational law, scientists can directly observe how these changes would affect cosmic structure formation. These simulations reveal the specific conditions necessary for the web to form and evolve as we observe it. One particularly revealing set of simulations explores universes with different amplitudes of initial density fluctuations. If these fluctuations were significantly smaller than in our universe, structure formation would be dramatically delayed, potentially preventing galaxies from forming before dark energy began accelerating cosmic expansion, halting further structure growth. If the fluctuations were much larger, matter would collapse into black holes too quickly, again preventing the formation of stable galaxies. Our universe appears to occupy a sweet spot, where the amplitude of initial fluctuations allows for optimal structure formation. Similar simulations exploring universes with different amounts of dark matter reveal a similar Goldilocks quality. Too little dark matter, and structure formation proceeds too slowly, too much, and normal matter is unable to separate from dark matter to form distinct galaxies. The ratio of dark to normal matter in our universally 5:1 seems finely tuned to allow for the formation of the cosmic web as we observe it. These simulations suggest our universe's parameters may be optimized for complexity generation through the cosmic web. Whether this optimization reflects a deeper principle, multiple universe generation, or simply the conditions necessary for observers like us to exist, remains an open question at the boundary between physics and philosophy. The absence of the cosmic web would also dramatically affect our ability to study the universe. Many of our most important cosmological discoveries came from observing large-scale structure. The web's pattern of clustering helped confirm the existence of dark matter, constrain the amount of dark energy, and test theories of cosmic inflation. Without these structures to observe, our understanding of the universe would be severely limited. Consider how our cosmic origin story would differ in a universe without the web. In our universe, we can trace our origins through an unbroken chain, from the Big Bang to the formation of the cosmic web, the collapse of gas within dark matter halos, the formation of stars and their synthesis of heavy elements, the creation of planets from these elements, and ultimately the emergence of life from complex chemistry. Without the web, this narrative would be fractured, with no clear pathway from cosmic origins to complexity. The cosmic web also affects our future. In our universe, the web continues to evolve, with matter flowing along filaments into clusters, galaxies merging at nodes, and voids expanding as the universe grows. This ongoing evolution shapes the environments where future life might emerge. Without the web, cosmic evolution would be much simpler and less conducive to generating new complexity in the future. Dark energy's acceleration of cosmic expansion is gradually freezing the cosmic web, preventing the formation of structures larger than those we observe today. This suggests we live in a special epoch after the web has formed, but before it has been pulled apart by accelerating expansion. Without the web, this cosmic epoch of structure would never occur, and the universe would transition directly from uniform density to eternal dilution. This temporal perspective reveals another crucial aspect of the cosmic web. It represents a temporary phase in cosmic evolution, a period when gravity has had sufficient time to organize matter, but before dark energy pulls this organization apart. We exist during this special time when the universe has maximum structural complexity. In the far future, as galaxies recede beyond their mutual gravitational influence, the web will gradually dissolve, leaving isolated island universes unaware of each other's existence. The web's impermanence underscores its preciousness. The cosmic conditions that allow for this grand structure exist only for a finite period in cosmic history. Without the Webber, if we live trillions of years in the future, after the web has dissolved, the universe would appear much simpler and less structured, its capacity for generating complexity significantly reduced. As we contemplate a universe without the cosmic web, we gain a deeper appreciation for this extraordinary structure's role in everything we observe. From the distribution of galaxies across billions of light years to the existence of planets capable of supporting life, the web's influence permeates cosmic evolution at all scales. It is not merely a feature of our universe, but a necessary condition for the universe as we know it. The thought experiment of a webless universe ultimately leads us back to a profound realization: we exist because the universe organized itself into a web. This structure, emerging from simple physical laws acting over cosmic time, created the conditions necessary for stars, planets, and ultimately conscious beings capable of contemplating their own origins. In the cosmic web, the universe has written its own story and narrative of increasing complexity, emerging from initial simplicity through the patient work of gravity across billions of years. In our next chapter, we'll explore whether the cosmic web might be more than just structure, whether it might, in some sense, be alive with energy flows, complex dynamics, and even information processing on the grandest scales. As we continue our journey, the web reveals itself as not merely a physical structure, but a dynamic, evolving system with properties that challenge our understanding of cosmic organization. Silent energies pulse through the cosmic darkness. Beyond the visible filaments and clusters that define the cosmic web lies another layer of reality, a universe, alive with invisible currents of energy, magnetic fields stretching across millions of light years, and particles moving at nearly the speed of light. This hidden dynamism transforms our understanding of the cosmic web from static architecture to living system, a structure not merely existing in space but actively processing energy on the grandest scales. The cosmic web we've explored thus far might seem like a static framework, a scaffold of dark matter populated by luminous galaxies, but this perspective captures only part of the story. In reality, the web thrums with activity. Gas flows along filaments at hundreds of kilometers per second. Shocks propagate through the intergalactic medium, heating gas to millions of degrees. Magnetic fields thread through the void, influencing the flow of charged particles. And cosmic race atomic nuclei, accelerated to nearly the speed of light, zip through intergalactic space, carrying extraordinary energies. These dynamic processes reveal the cosmic web as a system far from equilibrium, a structure that continuously processes energy, creating and maintaining complexity in defiance of entropy's relentless push toward disorder. In this sense, the web shares a fundamental quality with living systems. It maintains organization through constant energy flow, a cosmic metabolism operating across billions of light years. At the foundation of this cosmic vitality lies the flow of matter and energy along the web's filaments. Gas streams from voids into sheets, from sheets into filaments, and from filaments into clusters, converting gravitational potential energy into kinetic energy and eventually into heat. This gravitational energy cascade, operating across all scales of the cosmic web, powers everything from the formation of galaxy clusters to the synthesis of heavy elements in supernovae. The conversion of gravitational energy into heat occurs most dramatically at the boundaries between different components of the cosmic web. When gas falls onto a filament from the surrounding void, it creates shock waves, cosmic versions of sonic booms that can heat the gas from thousands to millions of degrees. These shocks are among the largest energy conversion mechanisms in the universe, processing enormous amounts of gravitational energy into thermal energy. Recent observations with X-ray telescopes have detected some of this shock-heated gas at the boundaries of galaxy clusters, where filaments feed into the densest nodes of the cosmic web. The gas in these regions reaches temperatures of tens of millions of degrees, hot enough to emit X-rays that our telescopes can detect. These observations provide direct evidence of the energy processing occurring throughout the cosmic web. But thermal energy represents only one form of energy flowing through the cosmic web. Observations of radio emission from galaxy clusters reveal the presence of relativistic plasma gas so energetic that its particles move at significant fractions of the speed of light. This plasma often forms enormous structures called radio relics and halos, extending millions of light years and tracing the shock fronts and turbulence where filaments feed into clusters. These relativistic plasmas reveal another aspect of the cosmic web's energy processing: particle acceleration. Through mechanisms still not fully understood, some particles within the web's gas are accelerated to extraordinary energies, creating cosmic rays that travel vast distances through intergalactic space. These particles carry so much energy that when they occasionally collide with Earth's atmosphere, they create cascades of secondary particles detectable by ground-based observatories. The most energetic cosmic rays detected possess energies millions of times greater than those achievable in human-built particle accelerators. The fact that particles with such enormous energies exist suggests the presence of natural acceleration mechanisms operating on scales far larger than individual galaxies. The shock fronts and turbulence within the cosmic web provide prime candidates for these acceleration sites. Complementing these energetic particles are the magnetic fields that permeate the cosmic web. Though incredibly weak, by terrestrial standards typically billionths or trillionths, the strength of Earth's magnetic field, these intergalactic magnetic fields extend across millions or even billions of light years, making them the largest magnetic structures in the universe. The origin of these cosmic magnetic fields remains one of astrophysics' great unsolved mysteries. Some theories suggest they were generated in the early universe, perhaps during cosmic inflation or the electroweak phase transition. Others propose they emerged later, seeded by the first stars and galaxies, and gradually amplified by dynamo processes operating within the cosmic web. Whatever their origin, these fields now thread through the entire cosmic web, influencing the flow of charged particles and the propagation of shock waves. We detect these fields primarily through their effect on polarized radio emissions from distant sources. As radio waves from distant quasars pass through magnetized regions of the cosmic web, their polarization rotates in a process called Faraday rotation. By measuring this rotation across many lines of sight, astronomers can map the magnetic field structure within the intervening cosmic web. Recent observations suggest these fields align roughly with the filaments of the cosmic web. This alignment indicates a deep connection between the web's structural properties and its magnetic configuration. The same processes that organize matter into filaments also organize the embedded magnetic fields. This correlation transforms our understanding of the cosmic web from a purely gravitational structure to a magnetohydrodynamic system where magnetic fields play an active role in shaping gas flows and energy transfer. The combination of flowing gas, magnetic fields, and energetic particles creates a system of remarkable complexity. Turbulence, chaotic, swirling motions spanning a wide range of scales permeates the gas within filaments and clusters. This turbulence transfers energy from large scales to small, creating a cascade similar to that observed in Earth's oceans and atmosphere, but operating across millions of light years. Cosmic turbulence serves multiple roles within the web's energy ecology. It provides pressure support against gravity, preventing some gas from collapsing into galaxies. It amplifies magnetic fields through dynamo processes, strengthening the weak primordial fields to their current values. And it accelerates particles to high energies, contributing to the cosmic ray population that permeates intergalactic space. This turbulent energy eventually dissipates as heat, maintaining the high temperatures observed in the intergalactic medium. Without this constant energy input, the gas would cool through radiation, eventually falling into galaxies or filaments. The ongoing turbulent heating maintains the gaseous component of the cosmic web in its observed state, preventing it from cooling and collapsing completely. Energy also flows through the cosmic web in the form of radiation light of all wavelengths traveling between sources and absorbers. The most energetic radiation, particularly X-rays and gamma rays, can travel vast distances through the cosmic web before being absorbed, carrying energy from regions of high activity to more quiescent areas. This radiative transfer represents another mechanism for energy distribution throughout the cosmic web. When high-energy radiation interacts with the intergalactic medium, it can ionize atoms, heating the gas and changing its chemical state. This process contributed to cosmic reionization, the period when the first stars and galaxies emitted enough ultraviolet radiation to ionize the previously neutral intergalactic hydrogen. This reionization fundamentally changed the cosmic web's properties, making it transparent to most radiation and altering how gas flowed along filaments. The cosmic web also processes energy through the growth and activity of supermassive black holes. These extraordinary objects, residing at the centers of most galaxies, convert the gravitational energy of infalling matter into radiation with efficiencies far exceeding those of nuclear fusion. When fueled by the gas channeled along filaments, these black holes can outshine their entire host galaxies, becoming visible across billions of light-years as quasars. The energy released by these active black holes doesn't remain confined to their host galaxies, but propagates throughout the surrounding cosmic web. Enormous jets of relativistic plasma, extending millions of light-years, inject energy and magnetic fields into the intergalactic medium. The radiation and particles from these jets heat the surrounding gas, preventing it from cooling and forming Starcer process called AGN feedback that regulates both galaxy growth and the thermodynamic state of the cosmic web. This feedback creates a self-regulating system where the flow of gas along filaments fuels black hole growth, which in turn heats the surrounding gas, reducing further inflow. This cycle establishes a kind of cosmic homeostasis, preventing both runaway galaxy growth and catastrophic cooling of the intergalactic medium. The result is a dynamic equilibrium maintained through energy flows spanning millions of light-years. All these processes, shock heating, turbulence, magnetic field amplification, particle acceleration, radiative transfer, and black hole feedback, operate simultaneously throughout the cosmic web, creating an extraordinarily complex system of energy flows and transformations. This complexity challenges traditional categories of cosmic structure, suggesting the web might be better understood as a networked system than a static framework. Some researchers have begun exploring parallels between the cosmic web and other complex networks, from neural structures to the internet. Like these systems, the cosmic web efficiently transports matter and energy across enormous distances. It processes information through the propagation of gravitational and electromagnetic influences, and it exhibits emergent properties that cannot be reduced to the behavior of its individual components. Though parallels with living systems shouldn't be taken too literally, they provide useful conceptual frameworks for understanding the web's dynamics. Like biological organisms, the cosmic web maintains its structure through constant energy flow, responds to environmental influences, and evolves over time. Its filaments serve functions analogous to a circulatory system, transporting matter and energy to nodes where complex processes occur. Perhaps most intriguing is the information processing capacity of the cosmic web. The propagation of gravitational influences throughout the web essentially computes the future evolution of cosmic structure. Perturbations in one region influence distant regions through both gravitational and electromagnetic interactions, creating a vast, interconnected system where everything affects everything else across cosmic distances and timescales. This perspective invites us to consider whether complex systems operating across such vast scales might possess emergent properties beyond our current understanding. While not suggesting consciousness or purpose, this approach acknowledges that sufficiently complex energy processing networks can exhibit behaviors that appear goal-directed or self-organizing when viewed at the system level. The energy flowing through the cosmic web isn't just relevant to abstract considerations of cosmic dynamics, but directly influences the formation and evolution of galaxies, including our own Milky Way. The gas that formed our galaxy, the stars within it, and ultimately the elements in our own bodies all flowed along filaments of the cosmic web, processed through the web's energy systems before becoming part of our local environment. As we continue mapping the energetic components of the cosmic web with increasingly sensitive instruments, new aspects of its dynamics continue to emerge. The Large Synoptic Survey Telescope will map the distribution of galaxies with unprecedented precision. The Square Kilometre Array will detect the faint radio emissions from magnetized plasma throughout the web. And next-generation X-ray observatories will directly image the hot, shock-heated gas that traces energy conversion within the web. These observations will refine our understanding of the cosmic web, not just as a structural feature, but as an active, energy processing system operating across the largest scales in the observable universe. They will reveal how energy flows from voids to filaments to clusters, how it converts between different forms, and how these processes maintain the web's observed properties against the universe's overall expansion. Understanding these energy flows also helps address fundamental cosmological questions. The temperature and ionization state of gas in the cosmic web provides crucial constraints on when and how cosmic reionization occurred. The distribution of hot gas helps resolve the missing baryon problem by revealing where ordinary matter resides. And the properties of shock-heated gas test our models of structure formation and the underlying dark matter distribution. Perhaps most profoundly, the energy processes within the cosmic web connect the largest scales of cosmic structure to the smallest scales of particle physics. The shock waves propagating through filaments, the magnetic fields stretching across voids, and the relativistic particles accelerated at cluster boundaries all represent the interplay between fundamental forces operating across an extraordinary range of scales. In this sense, the cosmic web serves as nature's largest laboratory for studying how basic physical principles manifest in complex systems. As we contemplate the cosmic web, alive with energy, remember that the network of filaments we've explored is not merely a static framework, but a dynamic system processing energy, maintaining complexity and evolving through cosmic time. The silent currents flowing through this grand structure connect everything within it, from the largest clusters to individual galaxies to the stars and planets they contain. We exist within this living web, made of matter that has flowed along its filaments and energized by processes that continue to shape its evolution. In our next chapter, we'll explore how the cosmic web influences the fate of the universe, how its structure will evolve as cosmic expansion accelerates, and what this tells us about the ultimate destiny of everything we observe. Time stretches forward into an unseen horizon, carrying the cosmic web toward its ultimate destiny. As we've traced the birth and evolution of the universe's largest structure, one question remains: what will become of this magnificent tapestry in the distant future? The answer lies in the ongoing battle between gravity's pull and dark energy's push, a cosmic tug-of-war that will determine not just the web's fate, but the ultimate destiny of everything we observe. The cosmic web we study today represents a snapshot in timey structure, still growing and evolving as matter continues flowing along filaments, galaxies merge at nodes, and voids expand between. But this evolution occurs against the backdrop of an accelerating cosmic expansion that will ultimately limit what gravity can accomplish. Understanding the web's future requires tracking how these competing influences play out across cosmic time. When astronomers first discovered the cosmic web's filamentary structure, they naturally wondered how it would evolve. Would gravity continue drawing matter together, eventually creating structures even larger than the superclusters we observe today? Or would the universe's expansion prevent such continued growth? The answer emerged in the late 1990s with a shocking discovery. The expansion of the universe is accelerating, driven by a mysterious force called dark energy. This acceleration fundamentally alters the cosmic web's future trajectory. In a universe dominated by matter alone, gravity would gradually slow the expansion, allowing ever larger structures to form as gravity pulled distant regions together. But dark energy overwhelms gravity on the largest scales, driving galaxies apart at an ever-increasing rate. This cosmic acceleration effectively places a size limit on gravitationally bound structures. Today's observations and simulations suggest that structures larger than roughly 1 billion light-years across will never form. The superclusters and giant filaments we currently observe represent the largest structures that will ever exist in our universe. In the distant future, these structures will not grow significantly larger, but will become increasingly isolated from one another as the space between them expands. Within gravitationally bound structures like galaxy clusters, gravity still dominates over dark energy's expansive push. These clusters will continue to grow by drawing in matter from their immediate surroundings and merging with nearby clusters. But eventually, they'll consume all available matter within their gravitational reach, reaching a maximum size beyond which dark energy prevents further growth. This limitation creates a freeze-out of cosmic structure, gradual transition from a universe where the cosmic web continues to evolve to one where its largest features become fixed and increasingly isolated. We live in a special epoch when the web is still dynamically evolving yet has already formed its major features. Future cosmic civilizations, emerging tens of billions of years from now, would observe a very different cosmic environment. The impact of dark energy on the cosmic web operates differently across scales. On the largest scales, those spanning billions of light years, dark energy already dominates, accelerating the separation between distant superclusters. On intermediate scale, hundreds of millions of light years, we observe a transitional regime where gravity and dark energy compete, with filaments still drawing in matter but at an ever-decreasing rate. And on smaller scales within galaxy clusters, an individual galaxy's gravity remains firmly in control, continuing to build structure regardless of the universe's overall expansion. This scale-dependent evolution creates a fascinating future for the cosmic web. The web won't disappear, but will gradually fragment into isolated, island universes, galaxy clusters, or groups that remain internally bound by gravity, but become causally disconnected from the rest of the cosmos as space expands between them. Eventually, light from distant clusters will become so redshifted by cosmic expansion that it becomes undetectable, making other regions of the cosmic web unobservable from any single location. Computer simulations tracking the far future evolution of the cosmic web reveal this fragmentation in striking detail. Filaments gradually empty as they feed their remaining matter into clusters. Voids expand to dominate the volume of the universe even more thoroughly than they do today, and the network structure of the cosmic web gradually dissolves into isolated clusters surrounded by ever-expanding empty space. This fate manifests most dramatically in the eventual isolation of galaxy clusters. Today, clusters regularly interact with their surroundings, receiving fresh gas and galaxies along connecting filaments. But in the distant future, tens of billions of years from now, these connections will be severed by cosmic expansion. Each cluster will become an island universe, containing perhaps thousands of galaxies but completely isolated from the rest of the cosmos. Within these island universes, evolution continues. Galaxies will merge until only a few giant ellipticals remain in each cluster. Star formation will gradually exhaust the available gas, leading to increasingly old stellar populations dominated by low-mass, long-lived red and brown dwarfs. Over incomprehensibly long timescale trillions of years, these stars will burn out, leaving clusters of dead stellar remnants orbiting in the darkness. The cosmic web's fragmentation has profound implications for the observable universe. Astronomers in the far future would have a radically different view of the cosmos. Within each isolated cluster, the wider cosmic web would become undetectable as light from other clusters, redshifts beyond observability. The evidence for the Big Bang, from cosmic microwave background radiation to the large-scale distribution of galaxies, would gradually disappear from view. This means that the cosmic web isn't just a structure, but a temporary window, allowing us to understand our cosmic origins. We live in an era when the web is still observable in its connected form, providing evidence for everything from dark matter to the Big Bang. Future observers, trapped within isolated clusters, would lose this broader perspective, making our current epoch particularly valuable for cosmological understanding. The filaments connecting today's cosmic web will meet varying fates. The densest filaments, those linking massive clusters relatively near each other, may remain gravitationally bound despite cosmic acceleration. These structures will continue guiding matter flow between their connected clusters, maintaining some semblance of the web's current function. But longer, thinner filaments will be pulled apart by dark energy, their matter either falling into the clusters they connect or dispersing into the expanding voids. Voids, already nearly empty of galaxies, will grow increasingly dominant in the cosmic volume. As filaments empty into clusters and cosmic expansion accelerates, voids will merge and expand, eventually comprising almost the entire volume of the observable universe. The rare galaxies that currently reside in voids will either be slowly drawn toward distant filaments or become completely isolated, evolving in near-total separation from other galaxies. The evolution of the cosmic web under dark energy's influence represents a transition from a universe organized by gravity to one dominated by cosmic expansion. This transition fundamentally alters the trajectory of cosmic evolution, moving from increasing complexity through gravitational organization to decreasing complexity through isolation and fragmentation. It represents a kind of cosmic middle-ager transition from youth to eventual senescence. For the Milky Way and its neighbors, this cosmic evolution has specific consequences. Our galaxy resides in the Local Group, a small collection of galaxies that includes Andromeda and several dozen smaller systems. This entire group sits along a filament within the larger Laniakea supercluster. In the distant future, the Local Group will complete its merger into a single massive elliptical galaxy, while simultaneously becoming increasingly isolated from the rest of Laniakea as cosmic expansion accelerates. About 4.5 billion years from now, the Milky Way and Andromeda galaxies will begin a series of close passes that will ultimately result in a complete merger. This local gravitational interaction will proceed regardless of the universe's overall expansion, as the two galaxies are already gravitationally bound to each other. The resulting giant elliptical galaxy, sometimes called Milkomeda, will eventually incorporate all the smaller galaxies in the Local Group as well. But while this local consolidation occurs, the Local Group itself will become increasingly isolated from neighboring galaxy clusters. The Virgo cluster, currently about 54 million light-years away and connected to us by a dark matter filament, will accelerate away due to cosmic expansion. Eventually, it will recede beyond our observable horizon, along with all other external structures. The Local Group will become its own island universe, cut off from the rest of the cosmic web. This progressive isolation occurs at different rates for structures at different distances. Galaxies within our Local Group are already gravitationally bound and will remain so indefinitely. The nearby Virgo cluster will eventually become unobservable, but not for tens of billions of years. More distant structures, like the Coma cluster or the Great Attractor, will disappear from view sooner, their light becoming too redshifted to detect as cosmic expansion accelerates them away from us. What makes this evolution particularly poignant is its irreversibility. Once regions of the cosmic web become causally disconnected by accelerating expansion, they can never reconnect. Information can no longer pass between them, creating permanent cosmic horizons. This isolation is fundamentally different from the current limitations of our observable universe, which are set merely by the finite age of the cosmos and the finite speed of light. The fate of matter currently flowing along cosmic filaments depends on its specific location. Matter near the densest regions of filaments, with sufficient overdensity to resist cosmic expansion, will eventually fall into clusters. Matter in less dense regions will become stranded as filaments stretch and thin, eventually finding itself isolated in the expanding void. The cosmic web thus acts as a sorter, determining which matter remains in bound structures and which becomes isolated in the expanding cosmos. This sorting process already operates today, but will become more pronouncedly binary in the future. The boundary between regions dense enough to remain bound and those destined for eternal isolation is called the cosmic watershed, a divided between the gravitationally bound and unbound universe. Matter on one side of this watershed will eventually become part of isolated cluster-scale structures. Matter on the other side will disperse into the void, never to form part of any bound system. The impending fragmentation of the cosmic web raises profound questions about the long-term future of complexity in our universe. Structures like galaxies, stars, planets, and potentially life itself depend on the concentration of matter and energy that the cosmic web facilitates. As the web fragments and isolated regions exhaust their resources, the universe may become increasingly hostile to complexity, with fewer new stars forming and fewer regions capable of supporting planetary systems like our own. However, this decline in complexity would unfold over truly staggering timescales. Even isolated galaxy clusters contain enormous reserves of gas that can form stars for trillions of years, albeit at ever-decreasing rates. The stars themselves, particularly the lowest mass red dwarfs, can shine for trillions of years longer. And even after stars exhaust their nuclear fuel, planets orbiting stellar remnants could potentially remain habitable through alternative energy sources like tidal heating or the faint glow of Hawking radiation from black holes. The cosmic web's evolution thus influences not just the structure of the universe, but its capacity to generate and maintain complexity over cosmic time. The web represents a temporary but essential phase in cosmic history, a period when gravity can create highly organized structures before dark energy pulls them apart. We exist during this special epoch when the web has reached its peak development, but has not yet begun its long decline. The philosophical implications of this evolution are profound. The cosmic web's eventual fragmentation suggests our universe has a finite capacity for organization and complexity generation. Unlike scenarios where structure continues growing indefinitely, our universe appears to have a maximum possible complexity that it has already approached or reached. Future evolution will see not greater organization, but gradual dissolution as cosmic acceleration overcomes gravity's organizational influence. This perspective aligns with views from thermodynamics and information theory about the universe's long-term evolution. While gravity temporarily creates regions of lower entropy by concentrating matter into structures like the cosmic web, the universe's overall entropy continues increasing. Dark energy's acceleration of cosmic expansion represents another manifestation of this tendency toward increasing disorder, overwhelming gravity's ordering influence on the largest scales. For hypothetical civilizations in the far future, the fragmentation of the cosmic web would fundamentally alter their understanding of the universe. Observers emerging in the distant future would see only their local galaxy cluster, with no evidence of the larger cosmic web, the Big Bang, or the universe's expansion. Their cosmology would be radically incomplete compared to ours, missing crucial evidence about cosmic origins and evolution. This realization has led some philosophers to suggest we live in a uniquely privileged time for cosmological understanding, an era when the evidence for our cosmic history remains observable before dark energy erases it from view. Our ability to see the cosmic web in its connected form, trace its evolution back to the Big Bang, and measure the universe's overall expansion represents a temporary window that future observers will lose as cosmic acceleration isolates different regions from each other. The web's evolution under dark energy's influence also affects how we interpret our observations of the distant universe. The galaxies and clusters we observe at great distances show the cosmic web as it appeared billions of years ago, when the universe was younger and more densely packed. As we look outward in space and backward in time, we see a cosmic web that was still maturing, with filaments and clusters still actively forming and evolution proceeding more rapidly than today. These observations of the younger cosmic web provide crucial constraints on cosmological models. By comparing the structure we observe at different cosmic epochs, astronomers can measure how the balance between gravity and cosmic expansion has evolved over time. This evolution directly constrains the amount and nature of dark energy, helping determine whether it truly acts as a cosmological constant or varies in strength over cosmic history. Recent observations suggest dark energy has maintained constant strength for at least the past several billion years, supporting the simplest model, where it represents the vacuum energy of space itself. If this model holds, the cosmic web's future evolution will follow the pattern described: early gradual fragmentation into isolated island universes, as cosmic acceleration overcomes gravitational attraction on larger and larger scales. However, alternative models where dark energy strengthens or weakens over time would predict different fates for the cosmic web. If dark energy weakens, gravity might regain dominance, potentially reversing the universe's expansion in a big crunch that would compress the cosmic web back into a singularity. If dark energy strengthens, it could eventually overcome gravity, even on small scales, tearing apart galaxies, stars, and ultimately atoms in a Big Rip scenario. Current observations favor neither of these extreme outcomes, suggesting instead a steady fragmentation of the web under constant dark energy. The web's fate is thus intimately tied to the nature of dark energy, the mysterious force driving cosmic acceleration. Understanding this connection helps explain why mapping the cosmic web at different cosmic epochs provides such valuable cosmological information. The web's structure and evolution directly reflect the competition between gravity and dark energy, making it our best large-scale probe of how these forces balance across cosmic history. As our maps of the cosmic web grow more precise through projects like the Dark Energy Spectroscopic Instrument, the Euclid Space Telescope, and the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, we gain increasingly detailed information about this balance. These observations allow us to project the web's evolution forward with greater confidence, refining our understanding of its ultimate fate. The picture that emerges from these studies is one of quiet, gradual unwinding. The cosmic web will not end dramatically but will slowly fragment and dissolve as cosmic expansion overwhelms gravity's organizational power on increasingly smaller scales. The process will unfold over billions and trillions of years, far longer than the current age of the universe. It represents not an ending, but a transition from a universe organized by gravity to one dominated by expansion. This gradual unwinding suggests a universe that continues existing indefinitely, though in an increasingly diffuse and isolated state. Unlike earlier cosmological models that predicted either endless cycles of expansion and contraction or a relatively rapid heat death, our current understanding suggests a much slower decline island universes of galaxies, gradually exhausting their resources over trillions of years, while the space between them expands forever. This fate, while perhaps melancholy from a human perspective, reflects the extraordinary story of the cosmic Weber structure that emerged naturally from tiny quantum fluctuations, evolved through the patient action of gravity over billions of years, and now enters the long, slow unwinding driven by dark energy. The web represents not just where matter is, but how it has moved and organized itself throughout cosmic history, a living record of the universe's evolution, from nearly perfect uniformity to extraordinary complexity. As we continue our journey through the cosmic web, remember that we observe it at a special time after it has formed its major features, but before cosmic acceleration has begun pulling it apart. This temporary configuration, held in balance between gravity's pull and dark energy's push, provides the conditions necessary for galaxies like our Milky Way, stars like our Sun, and planets like Earth. We exist during the cosmic web's mature phase, beneficiaries of the organization it has created and maintains. In our next chapter, we'll bring this cosmic perspective closer to home, exploring how our own Milky Way galaxy fits within the cosmic web and how its structure and evolution have been shaped by these larger cosmic forces. We'll discover that we are not merely observers of the cosmic web, but participants in its ongoing story: galaxy, our solar system, and we ourselves are part of this vast cosmic structure. Perspective shifts everything. From our vantage point on Earth, stars appear as isolated points of light scattered across the night sky. Our galaxy seems a distinct island of stars, separate from the wider universe. Yet this perception dissolves when we step back to observe the greater cosmic context. We are not merely observers of the cosmic web, but integral threads within its vast terrestrial galaxy, our solar system, our planet, and we ourselves exist as participants in its ongoing story. The Milky Way, that band of light stretching across our night sky, marks our view of the cosmic web from the inside. This spiral galaxy containing hundreds of billions of stars resides not in isolation but along a filament of the cosmic web, gravitationally connected to neighboring galaxies and flowing along invisible currents of dark matter that stretch across millions of light years. Understanding our place within this larger structure transforms our cosmic perspective from insular to interconnected. Our cosmic address begins locally but extends to the largest scales of the observable universe. Earth orbits the Sun, a relatively ordinary star located about 26.0 light-years from the center of the Milky Way, in one of our galaxy's spiral arms. The Milky Way itself forms part of the Local Group, a small collection of galaxies dominated by our galaxy and Andromeda. This entire group sits along a filament within the Laniakea supercluster, a vast complex of galaxies spanning more than 500 million light-years. Laniakea, whose name comes from Hawaiian words meaning immense heaven, represents one of the largest structures in our cosmic neighborhood. Discovered in 2014 through careful mapping of galaxy motions, this supercluster contains about 100 galaxies organized into filaments flowing toward a gravitational basin called the Great Attractor. Our local group resides along one of these filaments, slowly moving toward the supercluster's center under the combined gravitational pull of all its galaxies. But even Laniakea represents just one node in the broader cosmic web. It connects to neighboring superclusters through tenuous filaments of galaxies and dark matter, forming part of a network that extends across billions of light-years. Recent mapping efforts like the Sloan Digital Sky Survey have revealed our place within this larger structure, showing how Laniakea connects to other superclusters like Perseus Pisces and Coma to form the vast cosmic web we've been exploring. The Milky Way's specific position within this web has profoundly influenced its evolution. Our galaxy resides in what astronomers call a cosmic wall, a relatively dense sheet of matter between larger voids. This location has shaped the flow of gas into our galaxy, the frequency of interactions with neighboring galaxies, and ultimately the conditions that allowed our solar system and life to emerge. Unlike galaxies in dense cluster environments, where frequent interactions strip away gas and halt star formation, the Milky Way has enjoyed a relatively peaceful existence. Its position along a filament but away from dense cluster centers has allowed it to retain significant gas reserves and maintain steady star formation for billions of years. This stable environment provided the conditions necessary for the slow, undisturbed evolution of life on Earth. Yet our galaxy is not completely isolated. The Milky Way's location within the cosmic web connects it gravitationally to neighbors like Andromeda and more distant structures like the Virgo cluster. These connections create subtle but important effects, influencing our galaxy's rotation, the distribution of its satellite galaxies, and the flow of gas into and out of its disk. Recent observations have revealed that satellite galaxies orbiting the Milky Way are not distributed randomly, but tend to align along planes that correspond to the larger cosmic web. The most prominent of these, called the vast polar structure, contains most of our satellite galaxies arranged in a thin plane perpendicular to the Milky Way's disk. This alignment suggests these satellites flowed into our galaxy's gravitational influence along filaments of the cosmic web, rather than forming in place or being captured randomly. The flow of gas into the Milky Way also follows patterns dictated by the cosmic web. Astronomers have detected vast clouds of hydrogen falling into our galaxy from intergalactic space, providing fresh fuel for ongoing star formation. These gas flows are not uniform but concentrated along directions aligned with surrounding filaments. Through this cosmic accretion, our galaxy continues to grow and evolve, its fate linked to its position within the larger cosmic structure. Even our galaxy's internal structure bears imprints of its cosmic web position. The Milky Way's spiral arms, the distribution of its star-forming regions, and even the orbit of our Sun have been influenced by interactions with neighboring galaxies and the underlying dark matter distribution. The galactic barren, elongated structure of stars at our galaxy's center appears roughly aligned with the surrounding filamentary structure, suggesting the larger cosmic environment has influenced even our galaxy's internal architecture. This cosmic context extends to our solar system. The Sun formed about 4.6 billion years ago from gas that had already been processed through multiple generations of stars. The heavy elements that make up Earth and our body's carbon, oxygen, iron, and more were forged in previous stellar generations and distributed through the cosmic web by supernovae and galactic outflows. Our very existence depends on this cosmic recycling process, where matter flows through the web, becomes enriched in stars, and flows onward to form new systems. The Sun's position within the Milky Way, about 2/3 of the way from the galactic center in the Orion Arm, reflects this cosmic history. We orbit the galactic center at about 230 kilometers per second, taking about 225 million years to complete one revolution. During each orbit, our solar system passes through different environments within the galaxy, occasionally crossing spiral arms or regions of enhanced star formation. These galactic seasons may influence Earth's climate over very long timescales through variations in cosmic ray flux and encounter rates with interstellar clouds. Our solar system's orientation relative to the galaxy also connects us to the larger cosmic web. The plane of our planet's orbits is tilted approximately 60 degrees relative to the Milky Way's disk. This orientation affects how we view both our galaxy and the distant universe, determining which regions of the cosmic web we can easily observe from Earth and which remain hidden behind the galaxy's dusty disk. Even the history of the solar system bears imprints of larger cosmic web processes. The gas and dust from which our Sun and planets formed did not originate in isolation, but as part of a larger molecular cloud complex shaped by galactic forces. These forces themselves reflect our galaxy's interaction with the cosmic web, including gas accretion along filaments and dynamical effects from passing satellite galaxies. The cosmic web's influence extends even to the composition of Earth itself. The heavy elements that make up our planet were produced predominantly in massive stars and distributed through space by supernovae explosions. These stellar processes occur most actively in regions of enhanced density along filaments, and particularly at nodes where filaments intersect. Earth's composition thus reflects processes occurring throughout the cosmic web, concentrated and delivered to our corner of the Milky Way through the web's natural flows. Perhaps most remarkably, the atoms in our bodies directly connect us to this cosmic story. The hydrogen in our cells dates back to the Big Bang itself. The carbon that forms the backbone of our biology was fused in previous generations of stars. The iron in our blood was likely forged in ancient supernovae explosions billions of years ago. These elements journeyed through the cosmic web, flowing along filaments, cycling through stars, and eventually becoming part of our planet and ourselves. This atomic connection means we are literally composed of matter that has traveled along the cosmic web. The carbon atoms in your body may once have resided in stars on the opposite side of the galaxy, transported through space by supernovae explosions and interstellar winds before being incorporated into the molecular cloud that formed our solar system. We are, in a very real sense, children of the cosmic web, or matter assembled through its flows and processes. Astronomers can trace some of this history by studying the chemical composition of stars, including our Sun. Different elements and their isotopes serve as fingerprints revealing where and when the material formed. Some of our solar system's matter shows signatures of nearby supernova explosions shortly before the Sun's formation. Other components contain traces of neutron star mergers or massive stellar winds. These chemical signatures connect our local history to processes occurring throughout the cosmic web. Our consciousness of these connections represents something remarkable: the cosmic web becoming aware of itself through the emergence of intelligent life. The same forces that shaped the web's filaments also concentrated matter densely enough for stars and planets to form. The same flows that channel gas along cosmic highways also delivered the elements needed for biology. Through scientific observation and understanding, the web has generated observers capable of mapping its own structure and evolution. This self-awareness emerges most directly through our astronomical observations. When we map distant galaxies or trace filaments across billions of light years, we are the cosmic web studying itself. The light we capture in our telescopes has journeyed along geodesics, shaped by the web's mass distribution. The patterns we recognize reflect the same physical principles that govern our own galaxy's motion within its filament. Observer and observed are part of a single cosmic system. Our connection to the cosmic web also extends forward in time. The Milky Way continues its journey along its filament, gradually approaching Andromeda for an eventual collision about 4.5 billion years from now. This local interaction will unfold against the backdrop of the web's larger evolution under dark energy's influence. Our galaxy's future, and potentially that of any civilizations it hosts, is inseparable from the web's ongoing development. Even our observational perspective changes as our galaxy moves. The Sun orbits the galactic center, and the Milky Way itself moves relative to the cosmic microwave background at about 630 kilometers per second. This motion, largely dictated by our position within the local group and Laniakea supercluster, continuously changes our vantage point on the cosmos. What we observe today differs slightly from what observers would have seen millions of years ago, or will see millions of years in the future. Perhaps most profound is how our place within the cosmic web shapes our understanding of scale and significance. From Earth, human affairs seem all-important, planetary concerns vast, and cosmic matters remote. But recognizing our position within the cosmic web inverts this perspective. We exist as one small node within an incomprehensibly vast network, a single planet orbiting an ordinary star, itself one of billions in a galaxy, flowing along just one of countless filaments in the cosmic web. Yet this cosmic perspective need not diminish our significance, but can enhance it. The web's processes have concentrated matter and energy precisely enough to allow for stars, planets, and eventually conscious life. Its flows have transported and enriched the elements needed for complex chemistry. Its structure has created stable environments where intelligent observers could evolve and eventually comprehend the very web that created them. This represents not insignificance, but profound interconnection. Recent research suggests this connection between cosmic structure and potential habitability may be deeper than previously recognized. Galaxies along filaments appear to have more favorable conditions for planetary system formation than those in very dense clusters or isolated voids. The flow of slightly enriched gas along filaments provides the right balance of heavy elements, without the disruptive interactions common in cluster environments. Our location along a filament of the local sheet may be not just coincidental, but causally related to our existence. This relationship between cosmic structure and habitability extends to our galaxy's specific history. The Milky Way has experienced a relatively quiet merger history compared to many galaxies, with few major disruptions over the past several billion years. This stability, influenced by our position within the local cosmic web, has allowed for the sustained conditions necessary for complex life to evolve on Earth without catastrophic disruption. Even the local group's position within Laniakea may have significance for habitability. We reside in a relatively low-density region between major clusters, close enough to filaments to receive enriched material, but far enough from dense nodes to avoid frequent galaxy interactions. This suburban cosmic location may represent an optimal environment for life-hosting planetary systems to develop and persist over the billions of years needed for intelligence to emerge. As we contemplate our place within the cosmic web, we might naturally wonder whether other observers exist elsewhere among its vast filaments. The web contains trillions of galaxies, each with billions of stars, and potentially numerous planets. If our emergence as conscious observers reflects processes intrinsic to the web itself, the concentration of matter, the enrichment of elements, the stable environments created by its structure, then other observers may exist at similar nodes throughout its expanse. The vastness of the cosmic web ensures that even if intelligent life is extraordinarily rare, numerous examples likely exist somewhere within its structure. These hypothetical civilizations would each view the web from their own perspective, mapping filaments and clusters from different vantage points. Each would trace their own cosmic address, from local to global scales, discovering their own place within the grand cosmic structure. Would these civilizations reach similar conclusions about the web's nature and evolution? The physical laws governing the web's formation appear universal, suggesting observers anywhere would eventually discover dark matter's role, filaments' formation processes, and the web's eventual fate under dark energy's influence. The cosmic web provides a shared context potentially comprehensible to any intelligent observers, regardless of their specific biology or psychology. This universality suggests the cosmic web might serve as a natural common ground for different observing civilizations. Any technologically advanced species would likely map their surroundings, discover their position within the web, and reach similar conclusions about its physics and evolution. This shared understanding could potentially provide a foundation for communication, or at least mutual comprehension, should contact ever occur across the vast distances separating habitable worlds. Our connection to the web also provides temporal perspective. The web has evolved over billions of years to reach its current state, and will continue evolving for trillions more. Human civilization's entire history represents less than an eye blink in this cosmic timeline. Yet through scientific observation and understanding, we've managed to reconstruct the web's biography and project its future evolution. This represents a kind of temporal transcendence minds that exist for decades, comprehending processes that unfold over billions of years. This temporal perspective extends to our potential future as a spacefaring species. Should humanity eventually spread beyond Earth to other planets, solar systems, or even galaxies, our expansion would necessarily follow paths shaped by the cosmic web. Interstellar voyages would likely occur first along our local filament, where stellar densities are highest. Any hypothetical intergalactic journeys would almost certainly follow filaments between clusters, rather than attempting to cross the vast voids. Even our potential future among the stars would be shaped by the web's structure. More immediately, our ongoing astronomical surveys continue mapping the web in ever greater detail, refining our understanding of our place within it. Projects like the Dark Energy Spectroscopic Instrument are creating three-dimensional maps of millions of galaxies, revealing the filamentary structure across unprecedented volumes. These observations not only sharpen our cosmic address, but also constrain fundamental physics by measuring how the web has evolved under the competing influences of gravity and dark energy. Understanding our position within the cosmic web also connects abstract cosmology to our lived experience. When we observe the band of the Milky Way stretching across the night sky, we're seeing our view of the cosmic web from within the concentration of stars along our galaxy's disk. itself aligned with our local filament. The apparent motions of neighboring galaxies reflect our shared journey along filamentary flows. Even the cosmic microwave background radiation, with its slight temperature variations, shows the seeds from which the entire web, including our corner of it, evolved. This connection between cosmic structure and human experience appears in cultures worldwide. Many ancient creation myths describe the universe as a fabric or web, connecting all things. Indigenous Australian astronomy recognizes dark nebulae as celestial patterns complementing the bright stars. Numerous philosophical traditions emphasize universal interconnection rather than separation and isolation. These cultural perspectives intuitively captured something modern cosmology has confirmed: we exist as threads within a cosmic tapestry, not as isolated observers, separate from what we study. Modern physics further reinforces this interconnection through concepts like quantum entanglement and the causal structure of spacetime. The cosmic web is not merely a convenient metaphor, but reflects the fundamental interconnection of all aspects of the universe. The filaments connecting galaxies represent not just visual patterns, but causal relationships: matter flowing along gravitational gradients, light traversing curved spacetime, and information propagating through the cosmos. As we continue mapping our position within the cosmic web, we gain not just scientific knowledge, but existential context. We discover that our existence remains inseparable from the larger cosmic processes that created and sustain the web. The elements in our bodies, the energy powering our lives, and the stable planetary environment enabling our evolution all connect directly to the web's structure and dynamics. We are not merely in the cosmic web, we are of it, products of its processes and participants in its ongoing evolution. In our final chapter, we'll explore what this cosmic perspective means for how we understand ourselves and our place in the universe. We'll consider why the invisible still matter show structures we cannot directly see nevertheless shape everything we can observe, including, ultimately, ourselves. And we'll reflect on what it means to feel simultaneously small within this vast cosmic network, yet meaningfully connected to its grand ongoing story. Darkness holds the light. Throughout our journey across the cosmic web, one truth has emerged repeatedly: what we cannot see shapes everything we can. The invisible dark matter scaffolding underlying all cosmic structure, the tenuous gas filling the spaces between galaxies, the subtle gravitational fields guiding the motion of stars and gas, these unseen elements determine the visible universe's form and evolution. This final chapter explores why the invisible still matters, not merely as scientific curiosity, but as essential context for understanding our place in the cosmos. The most profound revelation of modern cosmology may be that the universe we observe directly, the stars, galaxies, and gas that emit or absorb light, represents merely the visible surface of a much deeper reality. Like travelers seeing only the peaks of mountains rising above a sea of clouds, we observe directly just a small fraction of what exists. The full cosmic landscape, dominated by dark matter and dark energy, remains hidden from direct view, yet fundamentally determines everything we see. This hidden architecture manifests most dramatically in the cosmic web itself. The luminous galaxies, tracing filaments and clusters, represent just a small fraction of the matter in these structures. For every gram of visible matter in the cosmic web, roughly 5 grams of dark matter provide the gravitational foundation. These galaxies shine like lights, strung along invisible wires, markers of a structure they trace but did not create. Our inability to see dark matter directly does not diminish its importance. Though invisible to our telescopes, its gravitational effects shape the universe at all scales. Dark matter determines where galaxies form, how they cluster, and how they move through space. It guides the flow of gas that fuels star formation and ultimately creates habitable environments. Without dark matter, the cosmic web as we know it would not exist, and neither would we. This relationship between the visible and invisible extends beyond dark matter. The vast majority of ordinary matter, protons, neutrons, and electrons like those composing our bodies, also remains unseen. Astronomical inventories consistently show that visible stars and galaxies account for less than 20% of all ordinary matter in the universe. The rest exists as diffuse gas filling the cosmic web's filaments, or floating in the vast voids between too tenuous to form stars but too significant to ignore. Recent observations have begun detecting this missing ordinary matter through its subtle effects on light passing through the cosmic web. X-ray telescopes have imaged the hottest, densest portions of this gas in galaxy clusters and some filaments. Radio observations have detected the neutral hydrogen tracing filamentary structure, and studies of fast radio bursts passing through the cosmic web have measured the cumulative effect of this diffuse material across billions of light-years. These observations confirm what cosmological simulations had predicted. The cosmic web contains not just dark matter and galaxies, but a complex gaseous component that records the history of cosmic evolution. This gas has been heated by shock waves, enriched by supernovae explosions, and shaped by the gravitational pull of filaments and voids. It represents a vast cosmic repository, holding most of the universe's ordinary matter and much of its evolutionary history. The invisible components of the cosmic web matter, not just for completing our cosmic inventory, but for understanding the processes that created and maintain the visible structures we observe. Stars form from gas that has cooled and condensed within dark matter halos. Galaxies grow by accreting material flowing along dark matter filaments. And the largest structures in the universe, the superclusters and great walls spanning billions of light-years, emerged from the gravitational influence of dark matter operating over cosmic time. Even the emptiest regions of the cosmic web, the vast voids comprising most of the universe's volume, exert crucial influence despite their invisibility. These underdense regions push galaxies toward filaments through a process called void evacuation. They shape the large-scale flow of matter throughout the cosmos, and their expansion rate provides one of our most sensitive probes of dark energy, the mysterious force accelerating cosmic expansion. This interplay between visible and invisible extends to energy as well as matter. The cosmic web processes enormous amounts of energy through mechanisms largely invisible to direct observation. Shock waves from infalling gas convert gravitational potential energy to heat. Turbulence cascades energy from large scales to small throughout filaments and clusters. Magnetic fields, stretching across millions of light-years, guide the flow of charged particles and influence gas dynamics throughout the web. We detect these energy processes primarily through their secondary effects: X-ray emission from hot gas, radio waves from accelerated particles, or subtle distortions in the light from background sources. Like detectives inferring a crime from its aftermath, astronomers reconstruct these invisible energy flows from the traces they leave in observable phenomena. This indirect observation has revealed the cosmic web as not merely a static structure, but a dynamic system continuously processing and transforming energy. The predominance of the invisible in cosmic structure challenges our intuitive understanding of reality. Human perception evolved to detect features relevant to survival on Earth: visible light, audible sounds, touchable objects. But the universe operates on scales and through mechanisms far beyond these evolutionary adaptations. The most fundamental aspects of cosmic structure exist in forms our senses never evolved to detect directly. This limitation has profound implications for how we understand our place in the cosmos. What we perceive as reality, the world of visible objects, and direct sensory experience, represents just a narrow slice of what exists. The cosmic web reminds us that the universe extends far beyond our direct perception, operating through forces and structures we can comprehend mathematically but never experience directly. Yet rather than diminishing human understanding, this recognition has expanded it tremendously. Through mathematical models, computer simulations, and indirect observations, we have constructed a coherent picture of cosmic structure that extends far beyond what our senses can detect. We have mapped dark matter distributions across billions of light-years, traced the flow of invisible gas through intergalactic space, and measured the subtle influence of dark energy on cosmic expansion. This achievement represents one of humanity's greatest intellectual accomplishments, comprehending the invisible architecture underlying everything we observe. What makes this accomplishment particularly remarkable is that it emerged gradually through the accumulation of subtle evidence rather than direct observation. Unlike the discovery of new continents or celestial bodies, which involved seeing previously unobserved objects, the discovery of the cosmic web's invisible components required inferring their existence from their gravitational effects. This process-building understanding of the invisible through its influence on the visible represents science operating at its most sophisticated level. The importance of the invisible extends to our understanding of cosmic origins and evolution. The visible structure of today's universe emerged from invisible quantum fluctuations in the early cosmos, amplified by dark matter's gravitational influence during cosmic expansion. The galaxies we observe represent not the drivers of cosmic evolution, but its products, visible manifestations of processes operating primarily through invisible components and forces. This evolutionary perspective reminds us that the visible represents the exceptional in cosmic structure. In the early universe, matter was distributed nearly uniformly, with variations of just one part in 100, 0. Most of the universe remains relatively uniform even today, with galaxies and clusters representing rare peaks of density within a much more diffuse cosmic sea. What catches our eye, the bright galaxies and clusters, constitutes the unusual case rather than the norm, reflecting our perceptual bias toward the luminous and compact. The invisibility of most cosmic structure also affects how we understand probability and significance. When we consider questions like the likelihood of life elsewhere in the universe, we must account for the vast invisible infrastructure that enables visible phenomena like stars and planets. Habitable environments emerge not in isolation but as consequences of processes operating throughout the cosmic web. Gas enrichment through stellar evolution, steady accretion along filaments, and stable environments created by the web structure. These considerations suggest that what matters in the cosmos often lies hidden from direct view. The conditions enabling our existence depend more on invisible dark matter distribution and diffuse gas properties than on the visible stars we see in the night sky. The cosmic web's unseen components provide the foundation upon which visible structures form and evolve. They represent not mere background but essential context for understanding everything from galaxy formation to potentially the emergence of life. This perspective offers philosophical insight into the relationship between appearance and reality. Throughout history, thinkers have distinguished between how things appear and their underlying nature. The cosmic web provides a powerful, modern example of this distinction. What appears to the naked eye as isolated points of light in the night sky actually represents nodes in an interconnected cosmic network, their positions and properties determined by invisible forces operating across billions of light years. Various philosophical traditions have anticipated this understanding in different ways. Plato distinguished between appearance and underlying form. Buddhist traditions emphasize the interconnection of all phenomena beyond their apparent separation. Indigenous knowledge systems often recognize patterns connecting celestial and terrestrial realms beyond immediate perception. Modern cosmology has not invalidated these perspectives, but given them new, specific content through precise observation and mathematical modeling of the cosmic web's invisible components. The predominance of the invisible also affects how we understand meaning and significance in the cosmos. If most of what shapes our universe remains invisible to direct observation, then meaning cannot derive solely from what we perceive directly. The significance of any phenomenon, from the formation of a galaxy to the emergence of life, must be understood within the broader context of the invisible processes that enable and shape it. The cosmic web provides this context, connecting visible phenomena to their invisible causes and conditions. For human observers specifically, the recognition of the cosmic web's invisible architecture transforms our understanding of our place in the universe. We exist not as isolated observers of a distant cosmos, but as participants in its ongoing processes. The dark matter shaping cosmic filaments influences the motion of our galaxy. The diffuse gas permeating intergalactic space contains atoms that may eventually become part of future stars and planets. The magnetic fields, stretching across millions of light years, guide cosmic rays that shower our planet. The invisible does not merely exist out there, but permeates and influences our local environment. This connection appears most directly in our own composition. The atoms forming our bodies originated in stellar processes operating within the cosmic web's structure. The carbon essential to our biology formed within stars that themselves formed due to gas flows along dark matter filaments. The iron in our blood likely originated in supernova explosions that distributed elements throughout the cosmic web. We consist of matter that has journeyed along invisible cosmic highways before becoming part of our planet and ourselves. Even our consciousness, the awareness, reading these words, emerges from physical processes operating within the cosmic context. The complex neural activity generating thought occurs within brains, composed of elements forged in cosmic processes. The energy powering this activity traces back to our Sun, itself one small conversion point in the cosmic web's vast energy processing system. Our most subjective experiences remain inseparable from the cosmic web's invisible architecture. This recognition does not reduce human experience to mere physics, but contextualizes it within the grandest structure known. Our thoughts, emotions, arts, and sciences represent some of the most complex phenomena yet observed in the cosmic web processes, through which the web itself becomes partially conscious of its own existence. Through scientific observation and understanding, the cosmic web has generated observers capable of mapping its structure and comprehending its evolution. The web's invisibility holds particular significance for scientific epistemology, how we know what we know. Direct observation represents just one epistemological approach, increasingly supplemented by mathematical modeling, computer simulation, and statistical inference in modern cosmology. Our understanding of the cosmic web emerges not primarily from seeing its structure directly, but from integrating multiple lines of evidence into coherent models that explain observable phenomena through primarily invisible causes. This approach, inferring reality beyond direct perception, has transformative implications beyond cosmology. It suggests the limits of naive empiricism that recognizes only what can be directly observed. The cosmic web demonstrates that reality extends far beyond what our senses can detect, requiring conceptual frameworks that incorporate mathematics, indirect measurement, and theoretical models to comprehend. What matters most in understanding our universe may be precisely what lies beyond direct perception. The invisibility of the cosmic web also influences how we communicate scientific understanding. Unlike discoveries easily captured in striking images or simple demonstrations, the web's invisible architecture requires translation through visualization techniques, analogies, and conceptual explanations. Communicating this understanding to broader audiences demands creative approaches that make the invisible conceptually visible without oversimplification. Modern visualization techniques have proven particularly valuable in this translation process. Computer-generated images showing dark matter distribution, simulations illustrating gas flows along filaments, and conceptual diagrams mapping galaxy positions within the larger cosmic structure all help make the invisible components of the web comprehensible. These visualizations serve not merely as illustrations but as essential tools for developing and communicating understanding of invisible cosmic structure. The scientific significance of the invisible extends to practical astronomical research. Future observatories like the Square Kilometre Array, the Roman Space Telescope, and next-generation X-ray missions are designed specifically to detect and map components of the cosmic web invisible to current instruments. These projects represent enormous investments, justified by the importance of understanding the invisible architecture underlying cosmic structure. They recognize that what we cannot yet see may matter most for comprehending our universe. Beyond scientific understanding, the cosmic web's invisible components affect how we conceptualize humanity's potential future. Any expansion of human presence beyond Earth would necessarily follow pathways determined by the web's structure. Interstellar journeys would likely proceed along regions of higher stellar density corresponding to our local filament. Any hypothetical intergalactic voyages would almost certainly follow filaments between clusters rather than attempting to cross vast voids. Even our potential cosmic future would be shaped by the web's invisible architecture. The web's invisibility also influences how we understand cosmic timescales. The structure we observe today emerged through processes operating over billions of years, most of which occurred long before humans evolved to witness them. The web's future evolution will similarly unfold over timespans far exceeding human experience. This temporal invisibility process is too slow for direct human observation, complements the spatial invisibility of dark matter and diffuse gas, reminding us that cosmic reality extends beyond not just what we can see, but when we can see it. Perhaps most profoundly, the cosmic web's invisible architecture offers perspective on the ancient philosophical question of whether reality exists independently of observation. The web's structure and evolution operated for billions of years before humans evolved to detect it, and continue operating in regions too distant for our instruments to observe. Yet through careful observation of limited regions and times, combined with physical principles we've discovered, we reconstruct this independent reality with increasing precision. This scientific realism, the recognition that reality exists and operates, regardless of observation, draws support from the consistent evidence for the cosmic web's invisible components across different observational approaches. The same dark matter distribution inferred from galaxy motions also explains gravitational lensing observations and matches predictions from computer simulations based on cosmic microwave background measurements. This convergence of evidence strongly suggests we're detecting aspects of an objectively existing reality, not merely constructing convenient models. At the same time, the cosmic web's invisibility reminds us of the limits of observation and the importance of theoretical frameworks. Without gravitational theory, the concept of dark matter would never have emerged to explain galaxy rotation curves or cluster dynamics. Without quantum physics and nuclear theory, we couldn't understand stellar nucleosynthesis, creating the elements flowing through the cosmic web. Theory and observation function as complementary approaches, each incomplete without the other, in comprehending the universe's invisible structure. As our journey through the cosmic web concludes, we return to our initial question: why does the invisible still matter? It matters because what we cannot see directly shapes everything we can observe. It matters because the majority of cosmic structure, both matter and energy, exists in forms invisible to direct observation. It matters because our own existence emerges from and depends upon processes operating through this invisible architecture. And perhaps most importantly, it matters because understanding the invisible transforms our perception of the visible world around us. When we look at the night sky after comprehending the cosmic web, we no longer see merely isolated points of light, but nodes in an interconnected network. We recognize that the space between visible objects isn't empty, but filled with dark matter, diffuse gas, magnetic fields, and energy flows, connecting everything we observe. We understand that our own galaxy, solar system, planet, and selves exist not in isolation, but as integral components of this vast cosmic structure. This transformed perspective doesn't diminish our significance, but contextualizes it within the grandest structure known. We exist as conscious nodes within the cosmic web, collections of atoms complex enough to contemplate the very network that created us. Through scientific observation and understanding, we transcend our limited direct perception to comprehend the invisible architecture underlying everything we observe. In mapping the unseen cosmic web, we discover not just the structure of the external universe, but our place within its invisible threads. As our journey through the cosmic web draws to a close, we return to the night sky with transformed vision. Look up once more. Between the points of light that scatter across the darkness stretches something profound and invisible architecture, binding everything we see and much we cannot. The galaxies do not float alone. They are held, threaded, woven. Across billions of light years, something silent holds everything in its place. You cannot see it, but it is there. What began as tiny quantum ripples in the earliest moments after the Big Bang has evolved into the grandest structure in existence here, cosmic web, spanning billions of light years, organizing matter into an intricate network of filaments, clusters, and voids. This web represents not just where matter is, but how it has moved and organized itself throughout cosmic history, a living record of the universe's evolution from nearly perfect uniformity to extraordinary complexity. As we've discovered, this web consists primarily of components invisible to direct observation. Dark matter forms the scaffolding, its gravitational influence guiding ordinary matter along preferred paths. Diffuse gas fills the spaces between galaxies, flowing along filaments and recording the history of cosmic evolution in its temperature and composition. Magnetic fields stretch across millions of light years, influencing the flow of charged particles through intergalactic space. And dark energy drives the accelerating expansion that will ultimately determine the web's fate. The luminous galaxies we observe directly represent merely the brightest threads in this cosmic tapestry, concentrations of matter, dense enough to form stars that trace the underlying structure. They mark the nodes and filaments of a much vaster network, like lights strung along invisible wires or ships following unseen currents. Their distribution and movement reveal the hidden architecture shaping everything in our universe. This architecture operates across all scales, The same gravitational principles guiding galaxies along cosmic filaments also direct planets around stars and moons around planets. The same elements flowing through intergalactic space eventually form the clouds, oceans, and living beings of Earth. The same physical laws governing the cosmos's largest structures also determine its smallest components. The cosmic web connects everything we observe through unseen threads of causality and composition. Our own place within this structure takes on new significance when viewed within this cosmic context. The Milky Way exists not in isolation but along a filament within the Laniakea Superclustera strand of the cosmic web, containing thousands of other galaxies flowing together under shared gravitational influence. Our solar system formed from gas that journeyed along this filamentary structure, enriched by previous generations of stars that lived and died within the web's architecture. Even we ourselves, the atoms forming our bodies, the energy powering our cells, the complex neural activity generating our consciousness exist as consequences of processes operating throughout the cosmic web. The carbon essential to our biology formed within stars that themselves formed due to gas flows along dark matter filaments. The iron in our blood originated in supernova explosions that distributed elements throughout the cosmic web. We consist of matter that has journeyed along invisible cosmic highways before becoming part of our planet and ourselves. In mapping and understanding this vast cosmic structure, humanity has accomplished something remarkable, comprehending the invisible architecture underlying everything we observe. Through careful observation, mathematical modeling, and theoretical insight, we have reconstructed a reality far beyond what our senses can detect directly. We have mapped dark matter distributions across billions of light years, traced the flow of invisible gas through intergalactic space, and measured the subtle influence of dark energy on cosmic expansion. This understanding doesn't diminish our significance, but contextualizes it within the grandest structure known. We exist as conscious components of the cosmic web collections of atoms, complex enough to contemplate the very network that created us. Through scientific observation and understanding, the web has generated observers capable of mapping its structure and comprehending its evolution. We are not merely in the cosmic web, we are of it, products of its processes, and participants in its ongoing story. Tonight, you rest in a universe still shaping itself one thread at a time. The cosmic web continues evolving, even as we observe it. Matter flows along filaments toward dense clusters. Galaxies merge at nodes where filaments intersect. Voids expand as the universe's overall expansion accelerates. Dark energy gradually overcomes gravity's organizational influence on the largest scales, setting the stage for the web's eventual fragmentation into isolated island universes billions of years in the future. Yet this evolution unfolds over timescales far exceeding human experience, billions of years for significant structural changes, trillions for the web's eventual dissolution under dark energy's influence. On human timescales, the web appears nearly static, its major features already established by processes operating throughout cosmic history. We observe it at a special time after it has formed its major features, but before cosmic acceleration has begun pulling it apart. This cosmic perspective offers both humility and wonder. We recognize our small place within an incomprehensibly vast structure, while simultaneously marveling at our ability to comprehend it. We see ourselves as both insignificant within the cosmic scale and deeply connected to its grandest processes. We exist within the quiet architecture of it, all participants in an ongoing cosmic story whose beginning we can trace and whose distant future we can glimpse. And no, even in the dark, you are never alone. The cosmic web reminds us that nothing in our universe exists in true isolation. Every galaxy, star, planet, and person exists within an interconnected cosmic context, influencing and influenced by the vast, largely invisible structure spanning billions of light years. The apparent emptiness between visible objects isn't empty at all, but filled with dark matter, diffuse gas, magnetic fields, and energy flows connecting everything we observe. As you contemplate the night sky, remember that you're not merely observing distant objects, but witnessing the visible manifestations of a much deeper cosmic reality. The points of light scattered across darkness represent nodes in an interconnected network held together by invisible threads. You are part of this network, a conscious collection of atoms assembled through cosmic processes capable of understanding the very web that created you. Sleep now, within the quiet architecture of it all. Rest in a universe still become evolving through processes that began billions of years before your birth and will continue billions of years after. Know that your atoms have journeyed along cosmic filaments, been processed through stars, and now temporarily form the consciousness contemplating these very processes. You are woven into the fabric of the cosmos, a thread in the grandest tapestry known.